Right. So let's see. See if I can get everybody's name this time. Louis, right? Luis? Louis. Louis, you like Louis? Okay. Eric and Nicholas and Andy and let me see. Did you guys swap? No, you did not swap. James and Bobby and Kenneth and let me get this right. Alan, and then Tom seems to be missing. I don't know where Tom is. And we've got Mike and Brank, or otherwise another Eric, and we've got Tyler. Okay, and I'm Chris as of last week. Some people were saying that they had a little trouble with the homework, but let's take a look at that first. Here's what we're going to do today. We're going to go over the homework, and then we're going to get into actually defining Newton's laws and then momentum and energy. It happens to be Chapter 2 and Chapter 3. Hopefully you guys got a chance to at least skim over those and read them if possible. Again, I think you're going to do very well in the class if you do read this stuff beforehand. Even if you don't understand it then, you'll see it again, and then you'll see it again on the homework, and so on and so forth. While I'm thinking about the homework, I think only like 3 or 4 of you guys were able to log on to the website Mastering Physics with the ID course. After this, if you haven't, let's try to do that. Hopefully you have your books with you with a little card in it if you haven't logged on to Mastering Physics. If not, you can do it over the next day or two. But I'd like you to do that so that because there's an assignment on there for going forward for the next couple days. And I can show you the problems if you don't want to do it online this time. But let's try to get everybody on board with that. Okay, are there any questions from last week, first of all, or Monday? No? Okay. All right, so let's go look at the homework. So we started with, I said to try the straight up and down and then the free fall, correct? Okay, let's just look at it. Did everybody at least attempt it? At least attempted it? Okay, good. That's really all I can expect right now. And I know some of you guys said you've never taken science classes or physics classes in particular, and some people have said, oh, I took it a long time ago. I understand it takes a little time to get back into some of this stuff. And keep in mind, we're trying to do stuff that you might not have thought about ever in your life before. So don't worry about it if you go, oh my gosh, I don't really understand it. Okay, so let's look. This says, the sketch is similar to figure 2.6 in the textbook, probably a different textbook actually. Assume negligible air resistance. Negligible means it doesn't exist. So we're pretending that this guy standing here is holding his breath because he's on some planet where there's no air and happens to have the same exact acceleration due to gravity as on Earth. Okay, there's Tom. All right, Tom, we're going to go over the homework first, if you can grab that and see. And I understand it was a little tricky for some people, so that's okay. All right, so it says table 1 shows the velocity data, meaning, what did we say velocity was? Speed with a direction, okay? And then notice there's some negative numbers in here. We didn't even talk about negative velocity, what that means, but the negative and positive just means the direction, up or down as it turns out. So we'll get to that. Okay, table 2 is for a greater initial velocity, complete it, and table 3 doesn't specify an initial velocity. So we're going to see what we can do here. All right, so on the first one, it says, notice it says the time starts at 0. We're going to try to do that always. Okay, time starts at 0, and it says the velocity goes 30, then 20, then 10. So what's this guy doing? He's throwing the ball up in the air, right? And after 1 second, it starts at 30 meters per second. Then it slows down to 20, then it slows down to 10, slows down to 0. Then it turns around and starts falling and goes 10, 20, 30, 40 and speeds up as if we had dropped a ball or something, right? Okay, so it says try to find the distance. Okay, so remember the other day we said the distance equals the average velocity times the amount of time that's gone by. Okay? So we should be able to think, all right, do we know how fast it's, or do we know the average velocity between 2 seconds that we're talking about, and do we know the amount of time, which in this case is just going to be 1 second going by? Fair enough? So let's look at the first one. So from 30 meters per second to 20 meters per second, what's the average of 30 and 20? right? 30 plus 20 divided by 2 is 25 meters per second. Okay? And how much time went by from 0 seconds to 1 second? 1 second, right? So if 25 meters per second times 1 second went by, how far did it go? 25 times 1? 25 meters. Does anybody get that? Got that? Okay, so you put down 25 in the little thing and we're good to go. Okay, now let's look at the next time. Now it's slowing down as it's going up because he's throwing it up in the air, slowing down. Okay, from 20 to 10, what's the average? 20 to 10. So the average is 15 meters per second. Okay, and how many seconds go by? From 1 second to 2 seconds? From 1 second to 2 seconds. Well, you could do it a couple different ways, actually. I was doing it from, let's do it the way you guys just said. Let's do it that way. Might be easier.
I'm sorry, I'm the one who did not speak, but you don't have to go by what I did.
Oh, no, actually, that's actually a good way to do it, because I didn't talk about doing kind of the inter one. Let's do from the beginning. So Nicholas has a really good point. Let's do it from the beginning. So if we start at 30 and then we go down to 10, what's the average now? 30 plus 10 is 40. Divided by 2 gives us an average speed of how much?
20.
20 meters per second. And now how much time is going by? 2 seconds. 20 meters per second, right, for 2 seconds. So 20 meters per second for 2 seconds gives us how much distance?
40 meters per second.
40, careful, how much distance? 40 meters, right. So we've got to be careful about what we're talking about there. Okay, so that's going to be 40 meters. So you can put in the little 10, 40 meters. Okay, anybody, well, even if you're lost right now, let's look at the next one and see if we can get the next one. We're going from 30 meters per second to 0 meters per second. So what's the average? 15, right? 15 meters per second. It actually is going down because it's slowing down, so the average speed is going to be less each time. And how many seconds from 0 to 3? 3 seconds, right? So this is going to be 15. We're going to change this to 15 meters per second. Tom, can you see if I write way over here? A little tricky. I'm sorry. 15 meters per second times 3 seconds gives us how much distance? 45 meters. 45 meters. Okay. Now, I think the easiest way to do this is to pretend, and this is the easy way, instead of saying, we could do it the other way. Well, let's try it both ways. But I think the easiest thing to do is to pretend that now we've started all over and we're just dropping it from the top. Because isn't it true that at the top of the little thing way up here, how fast is it going? It says how fast it's going. 0, right? So it kind of going, hey, it's going 0 right now. At that point, isn't it just as if someone dropped a ball? I don't know if you've ever tried this before. I tried this when I was a kid. Like my friend would stand on like the roof of his house, and I'd chuck a ball up to him, and he'd try to just like grab it right at the top, and we'd swap back and forth. And if you grab it right at the top, it's going like really slow. So it's, you know, it's like if you wanted to, you could, if you knew how high an arrow was going to fly, right? Or how about this, a bullet. If you knew how high, don't try this at home or in the military. If you knew how high the bullet was going to fly, and you went all the way up to the highest point where that bullet's going to be, and someone shot a gun all the way up there, by the time the bullet got up to you, you'd be able to go boop and grab it, no problem, right? All right, because of the, you know, that's the way it goes. Yeah.
It's like when you're riding a motorcycle up a hill and you jump to another level and you only drop about 2 feet.
Yeah, exactly. 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 That's exactly right. Or if you're on a swing and you like jump off right at the top, like really you're not going that fast. You're not going fast at all right at the top. Maybe you're going fast in one direction, but right at the top you're kind of stopped, so you kind of go down and it's, you know, you're not flying off.
So you're just losing velocity.
As you go up, you're just losing velocity until you get to 0, and then it's as if you dropped it. Okay, so let's try it let's try it this way first. I'll come over here so maybe you can see it over here. Okay, let's say we tried it we went from 30 to -10. I'm not sure this is going to work right, but let's see if this works. 30 plus -10 divided by 2. We'll see if this works. What's 30 plus negative 10?
10. 20 divided by 2.
Yeah, 30 plus negative 10 is 20, right? 20 divided by 2 is 20 meters per second. How many seconds have gone by from 0 to 4? 4. So, well, here's the problem with this. The problem with this is, well, let's see. So it's going to be sorry, 30 minus 10 is 20 divided by 2 is 10 meters per second average. No, sorry, 20. We had it right. No, I did it wrong. Yeah. 30 plus negative 10 is 20. Divided by 2 gives you 10 meters. That's what it is. 10 meters per second. For how many seconds? 4 seconds. That's 40 meters. Does that actually make sense on here? How high was it after 2 seconds? On your chart, just look on it. 40 meters. How high was it after 4 seconds? Haha. So it does work out, actually. Here's why it works out. When you go up like this and back down in a straight line, I'm just making it look like this. It doesn't matter whether it's negative or positive. Right. Remember that chart that, I don't know if you remember, when we started out the other day, I covered it up so you wouldn't know how far something falls. Does anybody remember how far something falls in 1 second?
9.8.
How much?
10 meters.
We got to remember this. Let's think about this. If I drop something, okay, after 1 second, how fast is it going? What did we say? We've been doing this the whole time. It's on the left-hand side. After 1 second, 10 meters per second. What's the average from 0 to 10? 5 meters per second average. The average. How many seconds goes by from 0 to 1? 1 second. So the distance something falls in 1 second at the beginning is 5 meters. Okay, so we said that it falls 5 meters. We said that the top, right at the top when it's at 0, is actually 45 meters high. And what did we say after 1 second before it got to the top? How high was it? It was 40. Notice that it's 40 here as well because it falls the same amount of distance it went up in the last second. It falls in the first second from the top. Okay? And so you don't even need to do the rest of this if you don't want to. Okay? What was, let's see, what was this one? It started, if it was 40, then this one was 25, right? And then it started at 0, right? 0 to 25 to 40. So this is going to be 40, and then what's it going to be after 25? And then back down to 0. And let's look, it's going to be 40, let's see, so it's going to be 25, back down to 0, okay? And let's look and see if it works. What's 30 plus negative 30? 0. So what's the average from the start to where it comes back to where it almost hits them again on the ledge? 0. And how much distance is 0 times 1? 0 meters. So see how it's back down to where it started? Now the next question is, it does continue to fall down. Okay, so we can do it again. We can do it a couple different ways. What's 30 plus negative 40? What's going on here? 30 plus negative 40 is negative 10 meters per second. What's the average? 2. It's negative divided by 2 gives you negative 5 meters per second on average. And how many seconds have gone by from 0 all the way to 7? 7. So what's negative 5 times 7? Times 7 seconds equals negative 35 meters. Okay, does that make sense? So that was kind of cool, okay? Now, I think given the time, we're not going to go through 2 or 3. But if you want to do that or you want to check it with me later, that's cool. Or if you want, you can even do it this week and then say, hey, can I check next week? And we'll take a look. Okay? So yeah, so that was a little bit more than what we had gone over, although I will say that we covered all those topics. We didn't cover negative numbers, but we did cover all the topics. So good job trying that, and good job doing that. All right, flip it over. Let's try the free fall one. This one's a little easier, actually, because it never goes up and down. It just goes down, right? So this one should be a little bit easier. Okay, a rock is dropped from the top of a cliff. A rock dropped from the top of a cliff picks up speed as it falls. Pretend that the speedometer and odometer, that's how far it's going, are attached to the rock. Show readings of speed and distance at 1 second intervals. So every second they show as another reading. Both speed and distance are 0 at time 0. So we're just dropping it. Okay? All right. Note that after falling 1 second, the speed is 10 meters per second, and it's fallen 5 meters. We just talked about that, right? The readings for succeeding seconds of fall are not shown and are for you to complete. Okay. So let's just put these down. So we know that it's 0 seconds and 0 meters. And then it says 5 meters at 1 second. Do you remember what the chart was before? After 2 seconds, we're going down to 6 seconds, right? 3, 4, 5, 6. Let's just practice this. At 2 seconds, what's the average? So actually, what's the speed at 2 seconds?
20.
Yeah, 0, 10, 20, 30, 40, 50, 60, right? So the speed is 20. What's the average from 0 to 20? 10. 0 plus 20 is 10. 20 divided by 2 is 10. Okay, 0 to 20 is 10. And the time from 0 to 20 is how many seconds? Sorry, 0 to 2 is how many seconds? 2 seconds. 20 times, or 10 times 2? 20 meters. Okay. Average from 0 to 30? 15. 15 times 3 seconds? 45 meters. 0 to 40, average? 20. 4 seconds times 20? 80 meters, right? And then 0 to 50, average? 25. 25 times 5 seconds? 125. And then 0 to 60, the average is 30 meters per second. For 6 seconds means 180 meters. Okay. Everybody get that? Now, we went through that one really quickly, but it's the same idea as you're always doing before. Same idea. Okay? All right.
If I simply follow the formula.
Follow the formula.
5 times squared.
You can do that. If you wanted to, you could do, right, we did that the other day. We said the distance equals 1/2 times g times t squared. You could have done the exact same thing. I like to do it the way we did it just so we keep getting the idea of what it is in there. But you could have done this for each one. Same thing. Okay, let's answer the questions there. And by the way, notice on the sheet, you can see the ball falling farther each time. It's not a constant distance. It's actually what we call an exponential distance increase. Okay. All right, so let's see. Let's answer the questions. The speedometer reading increases by the same amount, how much per second? 10 meters per second every second. 10 meters per second squared. This increase in speed is also called acceleration. Perfect. Yeah, look.
I'm just trying to figure out how you did that. You went really quick for me.
I did.
So on that, the t equals 2 seconds. I'm trying to just understand the concept.
All right, let's look at the 2 seconds right there one again. Okay, 2 seconds have gone by. When I drop something, how fast does it get every second? How much faster every second?
10 meters.
10 meters per second. And you should probably get used to saying 10 meters per second every second. Because remember, it's not 10 meters. I know this is that weird, like, oh boy, we're talking lots of different things. 10 meters per second every second. In other words, it's getting faster every second, right? Okay, so what's the average speed? If you started at 0 and you ended up at 20, what's the average speed?
10.
10, what's the units?
10 meters per second.
Perfect.
For 2 seconds.
10 meters per second average. Yep, that's fine. Now, in those 2 seconds, we know that it was 2 seconds went by. So the time, we can do it this way. We can say the velocity average equals 10 meters per second. And the time in this case is 2 seconds. We know, and you kind of know this already, if you go, we know that the distance equals the average velocity times the time. So in this case, 10 times 2 gives you 20 meters. And if you follow that along and do the same exact thing for each one, you'll find out that that's how we get the next one and the next one and the next one. Make sense? Okay. All right. Let's look at letter B. The distance fallen increases as the square of the time. And that one you can, what that means is if the time was 5 seconds, it would be 5 squared more distance. That's all that means. We'll talk about that a bunch of times in this course, about things that are distance or time squared, something like that. Yeah, Nicholas?
That was the reason, sir, why I
chose to do it that way?
To begin with, because I followed you.
Yeah, that's a good point.
I'm like, hold on, why am I doing it this way? There's two birds in one stone.
Right, you do kind of do two birds with one stone, but it's best if you remember how you're doing it. Like you said, it's just it does it. Good. So time C. If it takes 7 seconds to reach the ground, then its speed is how fast? 70 meters per second. Okay. And then the total distance fallen. This is exactly what we were doing before. Yep, 0 to 70. 35 meters average times 7 seconds gives you 245 meters. 35 or 45? 45, right. Okay. Now, keep in mind this would not happen on Earth because of air resistance. So this would not look quite like this, but we're pretending we're holding our breath.
Sir, would you
And
read the C for me, please?
C, if it takes 7 seconds to reach the ground, that's all the way at the bottom here. It would be one more thing down here. 7 seconds.
7.
Yeah, if it's at 7, right, then it wants to know how fast, and we know it's 10 meters per second, so it's just another 10, so 70 meters per second. And then the total distance, we could use your formula if you wanted to. 1/2 times 10 times 30 times 7 squared, if you wanted to. Comes out the same, turns out. And then finally it says the acceleration just before impact.
At the 7.
Acceleration is what?
Acceleration.
Yep. In other words, just before it hits. What's the acceleration? This is kind of a trick question. 10 meters per second squared. Why is it that? Because it's always that when you're in free fall. What's the acceleration when I drop it? 10 meters per second squared. What's the acceleration after 6 seconds? 10 meters per second squared. What's the acceleration always in free fall? 10 meters per second squared. So that's the way it goes. A little bit of a trick question, but that's exactly the kind of question I'd ask you on a test.
Wait, so velocity is increasing, but the acceleration stays the same?
It does. And let's think about why that's the case. We'll actually get to that in this chapter, believe it or not. But here's really what's going on. Gravity's pulling the same on it. Is anything else pushing or pulling on it? Whatever it is you dropped? Right? So I dropped this pen. The only thing, once I let it go, that's forcing it to accelerate is gravity. That doesn't change. Because the Earth is so huge and you're so close to it that actually does not change. So it's the same force. And we know that a constant force gives you a constant acceleration. We'll get to that in this chapter. Okay, so that's a good question because why does it do that? All right, any questions on the homework? Okay, sorry that was a little frustrating for some people.
So the 245 meters, you got it at the 7th second?
At the 7th second, yes. Yep, good. Okay. All right. Now let's move on to Newton's laws. Okay. I'm a mess right now. All right. Hey, Alan, you want to look behind you and make sure the little green light is on the thing that looks like this? Just right there. It's on the top. Yeah, just look on the top of that. Green light on? Perfect. Okay. All right. Okay, so you guys have all heard of Isaac Newton before? Happens to be one of the greatest physicists, mathematicians. He was a pretty good theologian and politician the world has ever seen. Well, he might not have been quite as good at the theologian stuff and the politics, but he was good enough to get elected to Parliament, et cetera, et cetera. And he was the first person to really set down concrete rules of physics. Galileo, who we talked about last week, also, he was the first one to really start doing experiments and thinking about this stuff, but he didn't quite get it. And it was probably because he just hadn't quite seen over the top of that hill. You know, that was really what it was. Newton came along, and by the way, you've all heard of the plague, right? The plague happened. Well, Newton was, I think he was in college at the time, ended up having to go home because of the plague. He didn't want to die like anybody else, right? Went home, sat around for 2 years, thought all this stuff up, ended up creating physics, basically, also creating calculus. He created calculus so he could do his physics. And we're not going to talk about calculus in here, except I might mention it every so often. But I know. Louis is like, hey, no, calculus is good. Calculus is cool. Once it's another one of those ones where it's really, it gets in your brain and you go, I don't quite get it. And then when you get it, you go, aha, I see how the world works. But Newton had to create calculus so he could do all of his physics, as it turns out. Anyway, brilliant guy, happened to be born on Christmas. Let's see, in the same year that Galileo died. Okay, brilliant, brilliant guy, and responsible for all this stuff that we're going to talk about today. Okay, all right. So let's see. There we go. All right, Isaac Newton is famous for 3 laws. Okay, Newton's first law, second law, and third law. Okay, we're going to talk about all those, and then you're going to have to be able to use them in some sense or another. We have already talked mostly about the law of inertia. Okay, we talked about inertia, which is, do you remember what inertia is? We talked about the other day. Bobby, what do you think?
Stuff we can't explain.
We can't explain why. We can explain how, right? And we can explain what, right? So Bobby,
What's at rest must stay at rest, and what's in motion?
There you go. What's at rest must stay at rest. What's in motion must stay in motion. That is actually more or less the law of inertia. But doesn't need a force to continue moving, absolutely. And remember that heavy things with lots of mass have lots of inertia, right? Those battery pack that I had a lot of mass, that had a fair amount of inertia. Now, not as much as this building, right? But much more than a tiny little bug. Right? Okay. The second law is this force equals mass times acceleration. We'll get into that in a few minutes. And then the third law is this cool one called for every force there is an equal and opposite force. I think this one's the hardest one actually to understand. Sounds very easy, but it gets a little confusing, and we'll work through that and figure it out. Okay. All right. Newton's first law. Every object continues in a state of rest. In other words, if it's sitting there, it sits there. Or of uniform speed, very important. Remember, constant speed. Uniform and constant are synonyms. Constant speed in a straight line. That's another tricky one. It doesn't even, remember what did we say is happening if you're turning going the same speed? Acceleration. Yeah, acceleration. So that means there must be a force on it, right? A net force on it. Okay. And then unless acted on by a non-zero force. Okay. So that's what the law of inertia says. And it was exactly what you guys all just told me. The law of inertia says that if you're at rest, you're going to stay there unless something pushes on or pulls on you. If you're moving at a constant speed, same thing. You'll just keep on moving until something pushes on you or pulls on you at the same speed in the same direction. Okay? Object in motion stays in motion. Object rest stays at rest. Okay? Not too tricky. We did a little bit of that the other day, and that's about it. The whole key here is that continues is the important part. Something continues in that same state of motion that what it's doing before. What's wrong, Louis?
Are
we?
we gonna have colors today?
Oh, colors, right? It's coming up. Okay, so the whole point is that it's continues thing. The plates and tablecloth demonstration we saw, whoosh, those plates and the plates and the silverware stayed where they were because they have inertia, and they just want to stay there. And there wasn't enough friction from the tablecloth. Trust me, if you'd used some other like a wool tablecloth or something, forget it. All bets would have been off, right? The plates would have been everywhere because there would have been much more friction able to affect it. But he probably used like silk or something, right? Okay, so that's what's going on there. And you have to be a little bit careful. And here's why. This is one that we're going to have to think about for a minute or two. The space shuttle. Unfortunately, space shuttles don't run anymore, right? The International Space Station, that's up there. Here's the Earth. Here's the International Space Station. Anybody know how many miles above the Earth it is?
3 or 4.
3 or 4 miles? That would be a little close. Go screaming past at 17,000 miles an hour, you'd notice. Try again.
30 or 40,000 miles?
30, 40,000 would be farther than our farthest satellites, actually. So no, it's actually, and one more guess?
15,000.
15,000? No, it's actually about 200. Which means that if you look up at night, and you can go online and find a website that'll tell you where the International Space Station is every night, you can actually go up and look and you can see a little light go across the sky.
Every hour?
I think it's about every 3 hours, but I'm not 100% sure. Yeah, I'm not sure. But anyway, point is it's going in circular motion around the Earth, right? If it's going in circular motion, there must be A what?
A force.
It doesn't have to be a constant speed, but it is a constant speed. But there has to be a net force. Anyone know which direction? If this is going in this direction, we'll call it counterclockwise. Which direction is the force on it?
Clockwise?
If it was clockwise, then it would probably be slowing it down, right? So you think the force goes here like this, and then down here the force goes like that? It's actually incorrect. And you wouldn't necessarily know that. What's that? There is a force. Otherwise, if there wasn't a force, when it's here, it would keep going like this in a straight line, right?
It's gravitational.
It's gravitational. Which way does gravity pull on you? Down, towards the center. Which way does... So let me draw this right here a little bit bigger so you can all see it. This is the Earth. Here's our spacecraft here. And it's going, right now it's going this direction. Well, guess what? It gets pulled this direction. And then it turns a little bit because it's getting pulled, right? And it happens to turn in the same circle. And then a little while later, it's right here, and now it's going this direction. Well, guess which way the force is? This direction, towards the center of the Earth still. And then it gets all the way over here, right? And it's going this direction, and it gets pulled this direction. Okay, so it's actually really bizarre. And Newton was the first one to figure this out, by the way. He said he finally figured out, in fact, the whole story about Isaac Newton with an apple falling on his head, he may have seen an apple, who knows what fell on his head. But basically he realized that if the apple's being pulled down, the moon is also being pulled towards the Earth. So you can replace this satellite with the moon, which, by the way, is 250 or 300,000 miles away, a long time away. But same thing, the moon is being pulled by the Earth this way, and then the moon is going this way, and then gets over to here, and then is pulled this way, and then gets over to here and is pulled this way, and so on. And by the way, this is where calculus would come in handy, because those tiny little differences is where you get the calculus part of it. It's a tiny little infinitesimal change every instant. But that's what's going on there. Now, let's pretend that some evil super being turned off gravity on Earth right when the space shuttle was right here. Okay, it's going this direction and being pulled this direction. Right now, somehow, it's impossible, but somehow, gravity goes away. Which direction would that go in? Straight down. Yeah, kind of.
Wouldn't that, like if the sun disappeared, then wouldn't all the planets go?
Same thing. The sun disappeared, yeah. Yeah. Now, as it turns out, if the sun became a black hole, nope, we'd still be going around it. Wouldn't be seeing it anymore, but it's still good. It's kind of cool. We'll get to that in astronomy in a few weeks. Okay? All right, but that's the idea here, that sometimes this whole inertia thing gets a little crazy. The reason spacecraft can orbit the Earth is because of inertia. Pulled towards the Earth, keeps going around. I didn't bring a little my little string and ball here. I think it's in the other room, but if you put a tennis ball on the end of a string and you flung it around your head like this, it's the exact same thing. Your hand is pulling on the string towards you, and the ball is going this way. You have to get it going by doing a little force in the circular direction, but once you keep going around in a circle, you're pulling in and it turns, you're pulling in and it turns, you're pulling in and it turns, and it's enough, your pull is enough to keep it going around in that circle. So it's kind of cool that way. All right, same sort of thing. Same as a bucket. Yep, that's yeah, that one's same thing. That's I should get a bucket. It'd be tough to do in here. Maybe we'll go outside and do it. But that's a good demonstration. Same thing. The reason the water doesn't fall out of the top of a bucket when you spin it around your head is because, well, partially because the water's going sideways, and also because you're pulling hard enough that it's got enough speed to hit the side of the bucket and not drop. Yeah.
You brought up astronomy and space and everything like that. Was there a meteor shower last night?
There's meteor showers every night. Whether you can see it or not, it's a different story. There might have been. I don't know.
We saw 3 different ones last night.
There you go. Yeah, that's cool. Meteors are.
There was one last night in
Was there?
North Carolina.
Oh, okay. Were you in North Carolina last night?
No.
Okay.
I was just a bar.
Oh, okay. All right. That's cool. Yeah. There you go. Tyler, you had a question.
Yeah, is there a name for it? Like there's centrifugal force, centripetal force?
Yep. You're absolutely right. There is. The force that's pulling in on a circular moving object is called centripetal force. Yeah. There's another one called centrifugal force, which is kind of like, it doesn't really exist, although we can, depending on what frame of reference, like that movie you're in, you can think of it as a centrifugal force. But it's not a real force. It's always when you spin something around or when there's gravity pulling a satellite in a circle, it's always centripetal, which means towards the center. That's where it comes from.
So that's what's also keeping us on the ground, right?
What's keeping us on the ground is not centripetal force. It's just simply that we're already, no, we're not orbiting, right? We do have motion in a straight line. So I guess it is centripetal force. Now that you mention it, yeah, I guess it technically is. We're not orbiting. We're going the same speed as the Earth. So yeah, in some sense, you could call it that. Yeah, I mean it's a little more subtle than that, but that's a good way to think about it. Okay, but anyway, Newton's first law: object in motion stay in motion, object at rest stay at rest, unless acted upon by a net force. Okay, and now we've got the ideas about why that's the case. Okay. Okay, here's some more examples. Slam the brakes on in your car. If you slam the brakes on in your car, okay, your body keeps going forward, right? And that's why if you're not wearing a seatbelt, you smash your head into the windshield, right? You're going at 60 miles an hour, and the car stops because it hits a brick wall. Well, your body, unless it's connected to the car, keeps on going at 60 miles an hour right into the windshield, and then it stops, and then it's blood and all that, right? So not good. Okay, but that's that. When you're rear-ended in a car, this one's a little different, and this one takes a little while sometimes to get. If you're rear-ended in a car, your head stays where it is because the car gets hit, and then your back gets hit by the seat. And if there's no headrest, well, your neck is just kind of, your head's here like this. So your neck goes boop, because it's really your body, it's really your head staying where it is. Your head doesn't go backwards. It's your body that goes forwards, is really what it is when you get rear-ended. That's the tricky part. It's your body that's going forward, and your head stays where it is, and it looks like, right, like that. And that's why you get whiplash when you get hit from behind. Okay? So this is why you get whiplash. Okay. We already talked about this the other day. The Voyager 1 spacecraft launched in 1977, still traveling away at the Earth, almost 40,000 miles per hour. No more rockets necessary. No more gravitational assist. It's just going. And it's going to go for the next million years or something, right? That is a net force on that plane, right? That loud noise is the net force pushing the plane through the air, right? Okay. And then, sorry you can't really see this, but if you're on an airplane and you flip a coin, the coin doesn't go flying back at 600 miles an hour to the people in the back. It just goes up and down because both of you are moving at a constant speed and there's no net force on it. So it just goes up and down. Okay? Newton's first law. It's kind of cool. Yeah, I know. That wouldn't be so cool, if the steward, the flight attendant had to tip your glass when she's pouring the Coke and it goes flying in. That wouldn't be good. It's, lots of things would be bad at that point. Now, if you're standing on the wing, different story, because there's lots of air that's not moving along at 600 miles an hour. All right, so that's that. Okay, so that was Newton's first law. Any more questions on Newton's first law? I would say that's probably the easiest one when it comes down to it, although there's some tricky things. Okay, Newton's second law. Newton's second law is a weird one because it's actually written in terms of a formula. Not a very hard formula, I don't think, but a formula called F equals ma. And I've always said if I ever own a sailboat, I'm going to call it F equals ma. I'll probably call it this though, because this is the one that makes a little more intuitive sense. What makes something accelerate? A force. What keeps something from accelerating a lot? Well, it could be friction, but in terms of its own what? Mass. Okay? So what this formula says is an acceleration A is caused by a net force, but somehow made to not be as big by the mass of that object. Okay? So let's just throw a number in there right now. let's say we had a force of 10 newtons, and by the way, Newton is the, remember how that's the name of the force? Because this guy Isaac Newton that we're talking about here, not only did he get a unit named after him, we use it for his formula, one of his laws. The force of 10 newtons, and if your mass is 2 kilograms, how much acceleration are you going to have? 10 newtons divided by 2 kilograms equals 5. Now, units-wise, you would say newtons per kilogram, which is also meters per second squared. Because it's just an acceleration. Okay? Yeah, it's mind-blowing. We're not going to worry all about how you define a newton, right? But it's just know that if you're trying to do accelerations, you should be doing it in terms of meters per second squared. Okay? All right, so anyway, 5 meters per second squared. Okay, what if I made the mass 4 kilograms? Let's do it this way. What if I made keep the mass the same. Let's say I made the force twice as big, 20 newtons. 20 newtons divided by 2 kilograms gives you what acceleration? 10 meters. So look, if you double the force, what happens to the acceleration? Doubles it. Now let's say we made the mass twice as much, 4 kilograms. What's 20 divided by 4 kilograms? 5 meters per second again, by the way. 5 meters per second. So if you double the mass, what happens to your acceleration? Decreases by how much? Half. Okay? We call this we say that acceleration is directly proportional to the force. In other words, if the force goes up, the acceleration goes up in the same amount.
But the mass goes up, the acceleration goes down?
Yes, the mass is an inverse relationship. If the mass is twice, it's half as much acceleration. Okay? But really, this is the formula you're going to have to use for your, let's say, your homework coming up here. Okay? If you're going to do any problems, it's just going to be, for acceleration, Newton's second law, this is what we're going to talk about. Okay? Formula says the acceleration directly proportional to the net force. And this is key. It is the net force. It's whatever you add up all the forces like we did the other day, going in different directions. You add them all up. That's the one you use to figure out what the acceleration is. Okay? And inversely proportional to the mass. Push harder, you get more acceleration. Make bigger, you get less acceleration. And if you make smaller, it's the other way around. You get big, more, less force, smaller. Got it? Newton's second law. Not so bad. Okay, let's see. So that's Newton's second law. And got some examples on it here. Let's see, I'm just going to try this one more time. Get it? Nope, I didn't get it. All right, this is what we just talked about. Force of your hand accelerates the brick. Okay, twice as much force, twice as much acceleration. Twice the force on twice the mass. Bring that up there. Twice the mass, oh, you can't really see it. Gives you half the acceleration. Okay? Twice the force on twice the mass gives the same acceleration. Same force on 2 bricks, half as much acceleration. Same force, 3 bricks with 1/3 as much acceleration if you have 3. So like double it, you get 1/2. Triple it, you get 1/3, etc. Okay? All right, so that's how we just talked about there. Now, remember how we said that if I take this pen and this book and I drop them both, they hit the ground at the same time. Correct. Now we have enough information to say why that's the case. Okay. Do you think gravity pulls on bigger objects more than smaller objects? Does gravity pull harder on a bigger thing? What do you think? You'd say no? Remember what your weight is. If you are eating too much at the chow hall and you get bigger and bigger and bigger, doesn't the scale tell you you've got more and more weight? And didn't we say that weight is the force of gravity? So somebody who's huge stands on a scale and has a really big force of gravity. The force is big. Somebody who's tiny has a small force of gravity. Okay, so let's get that through our brain. The bigger the mass, the bigger the force of gravity. Okay, let's ask Andy if he knows.
Of course.
Of course you do. Okay, Andy, you're standing on a scale, okay, and it says some amount, which is the force of gravity on you, right? And then you go to the chow hall for 6 weeks and eat everything in sight, and you get big, right? And then you stand on the scale. Is it going to be more or less or the same?
It's gonna be more.
More. Does that mean the force of gravity is more or less or the same?
The force of gravity?
Yep.
Should be the same.
The scale measures the force of gravity.
Right.
So if you're bigger, the force of gravity is bigger, right? So it is. So let's all get that clear. A bigger object, more force of gravity on it. Okay? Bigger objects, more force of gravity. In fact, if you're twice as much mass, you have twice as much force of gravity. Okay? What did we say if we have twice as much mass about the acceleration? It's half as much. So you ready for this? If the force is this big, let's say that the size of my little, well, if the force on this mass, for the little mass, the force is little and the mass is little, your acceleration is going to be like that, let's say. Let's just say that force is little, mass is little, acceleration is some number. If you make twice the amount of force because you have twice the amount of mass, if you do math, the 2's cancel out, it ends up being the same amount of acceleration. Aha! This book has more mass than this pen. Gravity pulls harder on this book than this pen. But this book has more mass, so it doesn't accelerate as much for that huge, bigger force. The pen has less mass, accelerates more for that amount of force. So guess what? They cancel each other out. That's why they fall at the same rate. That's another one that you got to think about it a little bit to get it through.
Last week you said the mass is always the same.
This book's mass is different than the pen's mass, right?
But the book's mass is the same in space, it's the same.
It's the same, yeah. It's just the book's mass is the same anywhere. But on Earth right now, gravity pulls really hard on the book and not so hard on the pen. But it's pulling harder on the book, but it's harder to accelerate the book because it has more mass. It kind of seems like a circular argument, but it's not. It's just saying your force of gravity goes up, and at the same rate as the mass, the acceleration is the same. Okay, I'm not going to hammer that in too much more, but just know the case. Yeah, Annie.
No, that's why I thought the force of gravity was the same. For like example.
But what changed when you ate more food?
The mass.
You got more mass. So the force of gravity goes up. Yep. That's how you gain weight, is you gain more mass, right? Because the force is bigger on you now. Okay. So that's how. So now we kind of maybe understand this a little bit. Maybe we'll go over this again at some point when we talk more about gravity. We'll definitely go over it again. Okay. All right. Okay. Now, you guys did you know that on the moon they did experiments when the first few guys were on the moon? We sent like 7 different missions to the moon. The Americans did. Nobody else sent anybody else to the moon, by the way. Go America, right? We sent a bunch of people to the moon, and they did these experiments on there. One of the experiments was this hammer and feather experiment. Okay, I don't think I have the one on the moon, although you can look it up on YouTube, and it's of an astronaut standing there with a hammer and a feather, and he drops them at the same time. And you can actually see them go foop to the bottom, to the ground on the moon at the same time. It's pretty cool. But I am going to, oops, did it again. Hang on. I'm going to show you if I can find it. You know what? I wonder if I downloaded it. I think I did. Hang on. Let's hope I did. Lectures. Boop. I know, really. Let's see. Extras. Falling with air resistance. No, that's not it. Oh no. Hang on. Where would it have been? Hang on. Video library maybe? Mythbusters. That's the one. You guys like Mythbusters?
Yeah, absolutely.
Okay. you know what we don't have here is the speaker. Yes, we do. Speakers. I forgot to set them up. Okay, so what we're going to show is a Mythbusters episode. Part of it, like 2 minutes. Not even. Sorry, 2 minutes. I'll give you a break pretty soon, too. And in this episode, they do this hammer and feather thing on Earth, which means they somehow have to get rid of the air, right? And the way they get rid of the air is by creating a vacuum. And they do that with some cool toys that they use. Okay, so let's see. All right, you want to hit the lights, Louis?
The really cool thing about a vacuum is that there's no air resistance. Something as light as a feather is going to drop the same rate as something as heavy as a hammer. So I should be able to put these in the vacuum and see them both hit the ground at the same time if it is a true vacuum.
In my left hand I have a feather. In my right hand a hammer.
Commander David Scott carried out his famous test to prove Galileo's hypothesis that all objects are affected equally by gravity. And as Carey explained, with no air resistance, they should fall at the same speed.
How about that? Mr. Galileo was correct.
So, as a control to confirm visually they're working with a vacuum, Carey rigs a clamp to drop them at the same time. And when the guys arrived at NASA in Alabama, the first test they set up for was the hammer and feather rig.
It's good enough. It's not like it's rocket science.
I don't think you can say that around here.
Well, I guess you're right.
The team seals the chamber, but for this control, they don't create a vacuum.
Atmospheric pressure in 3, 2, 1.
Cool. The hammer hit first. Perfect.
So the laws of physics still apply. I drop the hammer and the feather at atmospheric pressure exactly at the same time. Hammer hit first, feather glided down and hit last.
So after the air is removed from the chamber, Carey is ready to repeat the drop.
In 3, 2, 1.
That is so cool.
Yep, when there's no air resistance or drag, all objects are equally affected by gravity and fall at the same rate. So we do indeed have a vacuum. Of course, as most of you know, it's not a true vacuum, which in reality is impossible to create. But we did get a partial vacuum of around 10 to the -6 torr. A good approximation of what you'd find on the moon. And for more equally bizarre trivia on the missions to the moon, here's Adam and Jamie.
You know, when most people think about moon landings, they think about Neil Armstrong and Buzz Aldrin in 1969.
I know, they don't remember Michael Collins, the third astronaut on Apollo 11, who had to stay in the ship.
And also, what about the fact that the Apollo program lasted from 1961 to 1975?
Included over 38 astronauts, 12 of whom actually walked on the moon. The only time human beings have actually walked on another world.
As far as we know.
As far as we know. Okay, so there's your Newton's, thanks Lou. Newton's first and second, well, first law for that one. Okay, no worries. All right, so let's get back to here. And there we go. Okay, if the hammer and the feather fall equally side by side, would it be correct to say that equal forces of gravity act on both? What did we say? Which one's the guy, which is the one who went to the chow hall, the hammer or the feather? The hammer. So doesn't gravity affect the hammer more than the feather? So no, it's not true to say that equal forces of gravity act on the hammer and the feather. Trick question. Physics class is great for trick questions because you got to really think about it. And you got to say, okay, what do you mean? No, it's not the same amount of forces. Why does the feather fall? Because it's got less mass, for less force, same acceleration. Okay, you got to say that in your head 100 times. Okay? All right. Okay, so I tell you what, since Louis gone, let's take a break right now. I know my break slide is actually way up here because I took too much time, but there's my break slide. We'll take that, and we'll come back in 10 minutes if we could. Oh, of course, I just made you go out in colors again. All right. up? Yeah, you hit that off. That'd be great. Right in the top, right in the back. Right in the back. All right, let's move on. I had a little worksheet that I may hand out later, but I think in the interest of time, and this may happen often, we kind of spend a little more time in the homework, which is fine, than before. But we won't go over this right now. It's kind of more of the same stuff we were doing earlier as far as plugging and chugging numbers. But I did want to talk about cats and terminal velocity. So, turns out, and this, I've heard reports of this, so I assume that it's true. Cats actually, because the fluffy ones, not those ugly, like, non-fluffy ones, right? The Mr. Bigglesworth, right? The fluffy ones, if you drop them from high enough, because they're so fluffy and they've got so much air resistance because of that, they actually reach terminal velocity fairly quickly. In other words, the same amount of air friction up is the same as their weight, and they stop accelerating. And it's maybe at like 50 miles an hour instead of 150 miles an hour like a human, right? And if they spread out like cats kind of do when they're falling, it's even more. And they can slow down enough so that they hit the ground at a slow enough speed that they might not die. Now, if you dropped you almost made it. If you dropped a cat out of a plane or something, it doesn't matter if it's out of a plane or from like a 10-story building. They still can only go so fast. So supposedly, that's how a lot of cats survive some of these pretty high falls, right? So, well, tell you what, you start getting the cats. No, we're not doing that. But anyway, I wanted to just mention that at some point cats are kind of cool in that sense, the fluffy ones anyway. But okay, so we're not going to do that worksheet now. We're just going to go on to Newton's third law. Now I said before, Newton's third law is probably the trickiest one from the standpoint of understanding exactly what forces we're talking about. Newton's third law, talks about the fact that whenever we have a force, it's not alone. You can't push on something else without that thing pushing back on you. Okay, and that's very fundamental, right? And Kenneth is going, no, I'm not buying it. It's just a fact of the universe that forces come in twos and they come in pairs, no matter what. Why? Again, we don't necessarily know why, but that's the case. Okay. Push on the wall or push on your table. You can feel that force because you feel the wall. What is that feeling? That feeling is the wall pushing back on your hand. Okay? I'm standing on the ground. The ground is pushing up on me. Okay? I'm pushing on the floor here. The floor is pushing up on me. Keep in mind, those two forces are on different things. I push on the wall pushes on me. Two different things. Okay? A sledgehammer or a nail strikes a stake. The hammer pushes on the stake. The stake pushes on the hammer. That's why the hammer stops. You swing something through the air, the only way it's going to stop is if there's a big force pushing up on it. What's the force pushing up on it? The stake pushing up on the hammer. Okay? Kenneth is still looking at me like my head's spinning around here. Do you kind of get that idea? If I push on something, it pushes on back on me. If I pull on something, it pulls back on me. Okay? You pull a rope attached to a sled. Pulling on the rope, you can feel that the sled pulls back because it's hard to pull. Right? You pull it, it pulls back on you through the string, okay, called the tension in the string. Don't worry too much about that. But the whole point is, when you pull on something, it pulls back on you. A boxer punches a wall. Pow. The wall punches back on the boxer. Okay, you can't read this down here, but it says a boxer punches a piece of paper. Can the paper push back very hard? I mean, if you had a piece of paper like this and you punch it, why doesn't my hand break? like if I punched a wall with that huge amount of force because I'm huge. Right? It's both the difference in mass and the paper itself just can't push back. It goes through the air, right? So you punch the paper, right? The paper gives way and can't punch back as hard as you think you are pushing the paper. So it's actually, you're not punching that hard. You're actually not punching very hard at all when you talk about the thing, and that's why your hand doesn't break. If I punch the wall here hard, my hand would break, right? But if I punch paper, not so hard. So there's always two forces involved, and in things like punching a piece of paper, that force just isn't very big because the paper has no ability to push back if it's now, I put the paper on the wall and punch it, right? But then there's a bunch of things going on. I punch the paper punches the wall punches the paper punches my hand, basically, right? So it's a little more involved, but just suffices to say that there's always two forces going on when you punch something or when you pull on something. Okay? So far, so good? All right. Here's pretty much the definition. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Notice, if I'm punching the wall in this direction, the wall is punching me in the opposite direction. If I'm pushing on the floor down, the floor is pushing up on me in the other direction. Okay? Hey, Louis, we're working on Newton's third law now. So if you do want, you can maybe watch the video part later of what you missed, if you wanted to. Okay. So when we're talking about these forces, what we say is we call one of the forces what we call an action force. It's the force that kind of starts things off. And we say that there's a reaction force. Now really, there is no such thing as one force starting the other. But if you're punching your hand, you can say the punch is the action force into the wall. The reaction force is the wall punching your hand. Okay? All right. To every action, there's always an opposed equal reaction. Yeah, Mike.
It might be a dumb question, but with like the nail and the stake thing, if they're giving the equal amount of action and reaction, what's forcing that nail or that stake to actually go into the ground that is equal?
That is a great question. That's a great question, actually. Mike says, what's the force causing the stake to go into the ground? Well, the ground, have you ever tried to pound a stake into concrete? It's just not going to happen, right? The ground itself is able to give way, right? And so the force of the stake into the ground actually gets spread out a little in the ground and it goes into it. Why does it stop going? Because the ground is pushing up on it. But it's about different materials. So did that answer your question?
Yeah.
A little bit? If it didn't, that's fine too.
So
but
yeah, like punching the wall or whatever, it's giving equal force. So usually one's going to give in and you might dent the wall or you might break your hand. So how's that equal force? If you're an equal force to me, nothing would happen.
Good question. That's a good point. We'll get to that in a second in a different sense. But so Mike says, hey, wait, if I'm punching the wall and the wall dents, why does my hand dent? Well, your hand does kind of. It is an equal force, but what happens to the object itself because of that force is independent of the other object. So if I punch a wall, let's say I punch a pillow, right? If I punch the pillow, well, the pillow gives way because there was a force on it. My hand stops moving because there was a force on it. It might not hurt, but it stops moving because of that force. So that's a very good question. Seems like they would cancel each other out maybe, but they don't because they're on different objects. When I punch the pillow, all the pillow knows is, hey, I just got punched, right? If it could know anything. But my hand also knows, there was a pillow there, and you can feel it, right? I mean, if you closed your eyes and punched a pillow, you'd know that you punched a pillow. Why? Because there's a force on your hand from the pillow. So it's the two objects that do that. When you're hitting the stake into the ground, well, the stake gets hit from above. It hits back, but the stake doesn't care if it hits back. It just knows, I just got hit. And then it goes down, and then that force gets transmitted through the stake into the ground, which gets hit. And it's all the way down, really, in that sense. So we'll keep going over this a little bit. Okay. All right. Here's the easy rule to remember. Don't forget this. Object A exerts a force on object B. Therefore, object B exerts a force on object A in the other direction. Right? Object A exerts a force on object B. Object B exerts a force on object A. Because of that, they're together, two separate ones. Hammer pushes on nail. What's the reverse? Nail pushes on hammer. Okay, just think of it like that. Foot kicks ball forward. Ball pushes backwards on foot. You don't really want to say the ball kicks the foot, but if you wanted to, if you want to use the same verb, you can. Foot kicks ball forward, ball kicks foot backwards. That's why your foot doesn't go. Do you ever see all those videos where you miss the ball and your foot goes whoosh, right, and you fall over? That's because there's no ball there kicking back to stop your foot from keeping you going in a kind of a, fall over, right? You really do get pushed backwards, even though it doesn't necessarily seem like it. Book pushes on table, down on table. Table pushes up on book. Reverse it. Now I'm going to play a little game with you. Earth pulls down on human through gravity. Reverse it.
Human pushes back through gravity on Earth.
If Earth pulls down on you, what do you do to the Earth?
Push up.
Do you push up?
Push down.
You don't push down. I mean, you do through the ground, but that's different.
Pull up.
You pull up. Okay, this is weird. Okay, ready for this? Don't call me a liar quite yet. The Earth pulls down on you. You pull up on the Earth. Nobody ever thinks about that part of it, right? Gravity is a double force like anything else. Earth pulls down on you. You pull with the same force up on the Earth. Now, can I make it so this pen levitates because there's gravity? No. Can I make it so the Earth levitates? No. Why? Because the Earth is huge. Okay? It's like you trying to go out and move this building, right? You can push all day on it and it's not going to move because it's huge, right? Now, it's actually, if it was on ice, you probably could get it to actually slide a little, right? But it's huge. And the Earth is so huge that you can't measure how much you're pulling up on the Earth. But that's where it is. But if we do our little rule, we can make it work. Earth pulls down on human. Human pulls up on Earth. Isn't it the same? Earth pulls down on human. Human pulls up on Earth. You don't think you're pulling up on the Earth, but you are.
Because every time you lift your leg up, you're lifting it up with gravity. No.
Yes, I mean, if you jump up in the air, right, you're pushing down on the ground. What's the ground doing to you? That's why you go in the air, by the way. Ready to this? You push down on ground to jump. Ground pushes up on you and makes you jump. I mean, that's why you go through the air. That's how you do it. You push down on the Earth hard enough so the Earth pushes back and you go into the air. I mean, that's why you were able to jump. Okay? So this one is why Newton's third law is a little weird. And from what Mike said earlier, where he said, hey, how is the force equal if the stake's going into the ground and so forth?
What if you have the same objects, though? I mean, what was that theory? Because everything you're describing, you're talking about two different objects of different mass and everything else. What if you took that wall by itself and the same wall?
In outer space, they would start going towards each other. Not very fast. Gravity, as it turns out, you think of gravity as being a big force. Gravity is actually very weak, as it turns out. It's so weak that it takes the entire Earth to pull you down and hold you there, and then you can jump up off it really easily. The entire Earth keeps you from flying off the Earth, right? But you can still jump up pretty easily. That's how weak gravitational force is. But Mike, you're absolutely right. You're in outer space, and you had two pens that were identical, right? You had two pens that were exactly the same, and you stuck them in outer space with nothing else anywhere nearby. No planets, no stars, nothing. They would slowly go because they're pulling on each other, right? And then they'd finally connect like that. Probably bounce off a little and keep doing that. I mean, slow enough that it would take a while to even notice it. But yes, that's a very good point. We're talking about very different scales here when we're talking about the Earth versus you. Okay?
So are universes pulling towards each other?
Everything in the everything's pulling towards everything else. You're pulling towards the Earth. You're pulling towards me. You're pulling towards the computer, right? Your hat is pulling towards your head. But it's such a small amount that we never even notice it, except when we're talking about Earth-size objects. Okay? Gravity is such a weak force. It's why you don't worry about gravity when you're going around a corner. You don't think oh, I'm going around a corner near a big building, it's going to pull me to the side. No, because gravity is such a small force, right?
Is that why the universe is expanding? Because gravity can't keep
power of the Big Bang or whatever it was?
Good question. That's a very good question, and we don't really know the answer to that, to tell you the truth, although there's a lot of theories about it. The question was, is the Earth expanding because there's not enough gravity to hold it back, to pull it back together? We think that's the case, yes. Now, some people are, I'll leave it at that until a few weeks from now when we get to astronomy. Yeah, good. Okay, but everybody kind of, at this point, apply this formula, you'll never get a third law question wrong. Forget about it, and if you say Earth pulls down on human, human pushes down on Earth, no. You just had two forces like, the Earth, the down and down, they're not opposite, right? So you got to do it right. Earth pulls down on human, human pulls up on Earth. So, it's tricky. Okay. All right. You guys have all shot weapons, I assume. Maybe you haven't. I don't know if Nicholas, you've shot a gun before? Yeah. Yep. Shoot a gun. All right. There's a force on the bullet. The gunpowder from we can say the gun pushes on the bullet. Gun pushes forward on the bullet pushes backwards on the gun. This is why you have recoil on guns, right? Part of the reason. The rifles we all use, like M16s, they've got a lot of that is, what's that? Buffer. Yeah, there's springs in there and things that kind of buffer it. But for what it's worth, the force is the same. So the bullet gets the same force, which makes it hit a target 300 yards away, as the gun gets in the opposite direction. So why doesn't the gun go shoot something 300 yards the other way?
The gun has more mass.
Because the gun has more mass. So it's the same sort of thing. The same force. Here's our little force. It's this big, we're saying. The mass of the bullet is tiny. Remember, Newton's second law says that the acceleration is the force divided by the mass. Something big divided by something tiny gives you something big. 100 divided by 1 gives you 100, right? Same force, 100. Let's say the mass was 100. 100 divided by 100 only gives you 1. So tiny little acceleration on your gun, huge acceleration on your bullet. Same force. That's where Newton's third law comes into place. In fact, we used both laws there for this one. Okay, make sense? All right. Okay, we already skipped the break. Really quickly here, when we talk about these Newton's third law forces, it's really important to remember the system that we're talking about, because otherwise you'll kind of forget. It's kind of like this. If you're sitting in your car and you get and the car dies, so you can't go anywhere, why can't you push on the dashboard and make your car go forward?
You have no external friction.
Well, there's no external anything at that point. You're pushing on the dashboard. Newton's third law says the dashboard pushes back on you, right? Well, you're now pushing on the seat, and the seat pushes back on you, and the dashboard pushes back on you, and the dashboard's connected to the rest of the car. Everything actually cancels each other out inside the car. The only way you're going to get the car to move forward is to get out, push against the ground, and the ground pushes your whole thing forward. So it's all about the system we're talking about. So here's this little orange guy, right? And the orange is sitting in this cart. If the orange feels a force, who knows where it comes from? What happens to an object that has a net force on it? It accelerates, right? So the orange accelerates. Forget about the apple for a sec. It's got a force on it, accelerates. The apple pulls on the orange, and if this is the system, the orange accelerates. Okay? The apple actually is not really part of it at this point, but the apple gets pulled backwards. And have you ever tried pulling on something and you go a little bit this way and that comes towards you a little bit? That's what's going on. You're pulling on it, it's pulling back, and you kind of go towards each other. Now you both do end up moving, but that's it. So that's the system right there with just the orange getting pulled on. By the way, it's an apples and oranges like analogy, apples versus orange. All right. In the system, if now the system is now the apple and the orange, the whole system can't move on its own. And it's like this is the dashboard problem. The apple pulls on the orange goes this way, the apple goes this way. Inside this, nothing else actually happens here, okay? But look, on the ground, right, if the apple's pushing on the ground this direction, the whole system moves this direction, okay? The apple needs to push on the ground harder than it's pulling on the orange. Otherwise, it wouldn't go. There's got to be a net force on the apple. The only way the net force comes on the apple is if the apple's pushing on the ground harder so that it gets pushed harder this way than it's pulling on the orange.
The top part is connected to the bottom?
Think about the top part by itself. Okay? It's not going anywhere because there's no force, like as far as the system, there's no force in here that's making anything move outside of it. Now, once you say, okay, well, this actually should probably be outside this. Once you say, all right, I'm actually pushing on the ground, now the whole thing can go this way. It's kind of like, the real point of this is, how do you get going if you're pulling something? How do you go that way? Because you're pulling this way and the force on you is back that way. Well, guess what? Your feet are attached to the ground. Ever tried pulling anything on ice? It's almost impossible, right? You slip and slide because you're trying to pull and you just can't get any traction on the ice to move forward and you push against the ground. Okay? So think about that. And there's one more on this one, I think. Nope, no, there's not. So I don't want to stress, I don't want to spend too much time on this, but just know that you got to figure out which part of the picture you're talking about before you consider some of these forces. Okay? All right. So that, by the way, is chapter 2. Newton's 3 laws. First law was which one? Inertia, law of inertia. Object in motion stays in motion. Object at rest stays at rest at a constant speed unless acted upon by a net force, outside force. Yep. Good. Newton's second law was what? Acceleration equals force divided by mass. Good job, James. Acceleration is force divided by mass. Okay? Or force equals mass times acceleration, but same formula. And then Newton's third law, action versus reaction. Punch a wall, it punches back. Okay? All right. So now we're on to chapter 3, which is on momentum and energy. Okay? We start talking about momentum. It's actually slightly simpler, but it's related to energy, but it's a different concept, and we'll talk about exactly what it means. But let's think about it this way. And momentum, by the way, has a lot to do with inertia as well. You will hopefully agree that it is harder to stop a giant truck moving at some speed than it is to stop a small car or a skateboard or something like that moving at the same speed, right? Because of the mass and because of inertia, right? What we say is simply that the truck has more momentum than the car. In other words, the truck is bigger, at the same speed, it has more momentum than the car does. Okay? What we mean is really inertia in motion. The inertia is going along, the mass is going along, and it's got some amount of what we call momentum. Okay? And what we do is we say we define momentum as just the mass times the velocity. Okay, remember again, what did we say velocity is? Speed in a direction. So it's got a direction, right? That means momentum, which is mass times velocity, also has a direction. So if I'm going 10 miles per hour this way, okay, all right, my momentum is so much amount, that direction. If I turn around and go 10 miles per hour this way, my momentum is now in that direction. Two different momentums. Might be the same amount, what we call the magnitude, but it's a different momentum because of the direction. So momentum is a vector, just like velocity was. And acceleration too, by the way. Okay? All right. What we do, mass times velocity, we use m for mass, of course, because it's m. We use v for velocity, of course, because it's v. We use p for momentum because it's p.
Why p though?
Who knows why p? There's lots of, if you look up online, why do we use p for momentum? All sorts of weird theories about that. Something to do with Latin and this and that. And well, mass was already taken, so we can't use m. So why p? I'm not going to get into it, but who knows? Just know that if you ever see p, call it momentum. Okay? I don't know why. Don't know why. Okay? M was already taken, I guess. Can a car have more momentum than a truck?
Yes.
How?
It is at a higher velocity.
Higher velocity, right? Okay, how much momentum does a truck have when it's at a stoplight? Zero, except in Djibouti where there are no stoplights. They're always moving. No, zero. It has zero, of course, because zero velocity times whatever its mass is just zero. Okay? So sure, a car can have more momentum than a truck. Okay? All right. So the next thing when we're talking about momentum is we know that more mass, more momentum, more velocity, more momentum, both a direct relationship, by the way. Direct meaning bigger mass, bigger momentum, bigger velocity, bigger momentum. When momentum changes, normally we don't change the mass. Okay? Sometimes you change the mass. If you're sitting in a car and you, I don't know, throw stuff out of it, that whole car system is getting lighter, so its mass is actually changing. Right? Okay? But most of the time we keep the mass the same. If the velocity changes, didn't we say that a change, by the way, we used that term one yet? I don't think we have. The little triangle means delta, also means change. So triangle means change, and if you ever see me use delta V, that means the change in velocity. Okay? I'm trying not to use it too often, but change in velocity. A change in velocity is just the acceleration. Why do we know that? Because we already talked about that. What three things in your car change your velocity? Steering wheel, brakes, accelerator. And what happens when you change your velocity? You accelerate. Right? So, change in velocity is your acceleration. So if your velocity changes, it's just an acceleration. Okay? What causes accelerations, we already said? Forces cause accelerations. So we get more force, more acceleration, more change in velocity. And what it really depends on, though, well, it also depends on, I should say, is how much time the force acts. So if you had a rifle with a barrel this long, okay, the bullet, if you shoot the gun, the bullet will actually go, like, let's say 300 or 400 yards, or 300 or 400 meters, right? The bullet will go that far. If you were to saw off the front of that rifle, you know how, would the bullet go farther or less far?
Less.
Actually go less far. However,
there are a lot of factors involved in that.
there are lots of factors involved in that. But the main factor, I will argue, although I don't know that much about rifles, the main factor is that the gases that are pushing on that bullet in a long barrel have more time to push on the bullet to accelerate it more. And it's just a matter of accelerating it more. That same force for a longer amount of time accelerates it more. Okay? So we got to think about this force times time. Okay? When you have a force on an object, you change its velocity or you accelerate it. Okay? The amount of time gives it more time to accelerate, so you have a higher change. This force times time is also called a change in momentum. And why does it change your momentum? Let's think about this. Momentum is how fast you're going for your mass. If now you're going faster, have you changed your momentum? How did you go faster? You put force on it for some amount of time. Okay. That's laying it out there for you. Now we got to just get into a couple more details.
I thought we were done with that.
That wasn't math. That was like arithmetic, right? Force times time. That's what I've done. So far we've done multiplication, addition, maybe a little division, subtraction, and we didn't even do a square root, but we did a square.
That's math.
That's
I'm pretty sure that's math.
It's a little bit of math. But I only told you we'd do a little bit of math. Not that much. I said we'd do a little. But in order to in order to talk about some of these things, we do have to just get it in our heads. It's all about the concepts in the end. Okay. Let's walk through this. This impulse, we said, it's called impulse. And impulse just means force times time. The amount of force times the amount of time gives us our change in momentum. We've slowed down or sped up for the same amount of mass. And in other words, force times time equals the change in momentum. Now, we can actually derive this if we wanted to. Okay, I'm not going to do that because you're already whining about the math. Okay, right? But you could, knowing that acceleration is just the change in velocity, which we talked about. Okay, leave it at this. Here's what you need to really know about this. If you know that something has a force on it for some amount of time, it's going to change its momentum. That's all there is to it. And momentum is the mass times the velocity. Okay? All right. We call this the impulse-momentum relationship. Why? Because this is impulse, force times time, and this is momentum, mass times velocity. All right. That's that. Now, we're going to use this in a minute, and I'll show you why. Okay? Case number 1. Apply the greatest force. If you want to increase something's momentum, let's say in sports, like you're playing golf or baseball, right? Apply the greatest force for as long as you can, and you will end up with the ball going the farthest. Okay? When you hit a golf ball, right? I don't know if you've ever seen it, but there's pictures online where the golf ball gets squashed.
Page 63 actually has.
Oh, does it? Page 63, yeah. What's going on is the ball is getting squashed by the club face, yes, and it's taking time. The time that it's touching the ball is the time the force is acting on it. And so if you get a nice squishy ball, it squishes and it takes more time to act on the ball, and you can actually get it to go farther. It's part of the reason. Part of the reason it goes farther too is because of the little dimples on it, but I don't really understand all that. It's all about kind of keeping the air from like pushing directly back on it. Yeah, yeah. That's where you might want to increase the momentum fast. If you want to decrease the momentum over a long time, many cases you want to do this. Many cases that depend on your health. Let's say you're in a truck and it's out of control. I don't know if you guys have ever seen this before, but if you're going down a big hill, sometimes there's signs that say emergency truck exit ahead. What it is it's like a big long, generally up ramp full of sand. Okay? And if you're going down a hill in your truck and you've been using the brakes too much and the brakes fail, and that happens in trucks sometimes, right? You don't want to keep speeding up until you run into something hard like a wall or another car, a truck, or something like that. The better idea is to slow down, instead of by hitting something really fast, to slow down nice and gradually by like going into deep sand, maybe up a ramp. The longer time it takes to stop you, the better for your health and the health of the truck. Okay? Because either way, let's say you're going 100 miles per hour down this ramp. Right? Yeah. 100 miles per hour to 0 miles per hour. Okay? Let's do it this way. We'll actually just because Louis likes it so much, we'll use some real numbers here. Let's say you're going 100 meters per second, and your mass is, that's your velocity, and your mass is, let's say your mass is 10 kilograms. Okay? 100 meters per second, 10 kilograms. What is your momentum? Mass times velocity. 100 meters per second times 10 kilograms gives you 1,000 kilogram meters per second, which is our unit for momentum. Don't worry about that. If you end up stopping, what's your momentum? When you stop, what's your momentum? 0. So what is your change in momentum? You've gone from 1,000 to 0. What's your change? 1,000. Your change is 1,000 kilogram meters per second. Whether or not you stopped like that or whether you stopped by hitting a thing of sand and doing it over 10 seconds. Isn't it true that your change in momentum is the same? It's still 1,000, no matter if you stopped in 1 second or 10 seconds, right? Which one is better for your health? The one where you do it in 10 seconds, okay? Because it's going to be the same amount of, it's going to be the same change in momentum. A longer time means it's less force to stop you, okay? So, Louis, there's all your math, just for you. The reason you want to stop slowly is so that it doesn't cause a huge acceleration on you, okay? Here's another one, airbags. In your car, if you hit a brick wall, the airbag goes poof and expands really fast. But it doesn't stay expanded. That would actually be bad. Okay, we'll talk about that in a second. It deflates. So you hit the wall, the airbag goes up, your face hits the airbag, and then it goes poof, right? And there's powder and whatever. But while it slows you down much, much slower than hitting the windshield. Because the windshield, you stop like that, right? Yeah. In the airbag, you stop like this, poof, right? You don't go smack, you go poof. It feels like it. I mean, it absorbs the impact. Why does it absorb the impact? Because it's a longer amount of time and a much less amount of force. Again, if you're going 100 miles an hour and you hit and you stop, the amount of time for your face to stop is the really important part. If it's a very short amount of time, it means it's a huge force, and a big force in your face causes you to die from brain injuries, right? A bigger time means less force, therefore you tend to live. Okay, that's why airbags do their thing. Okay, that's why we have them. Okay, it's kind of a cushioning effect. If the airbag, okay, Louis, more math for you. We said that we went from 1,000 kilogram meters per second, and by the way, let's say we're going this direction, 1,000 kilogram meters per second that way. If we were to bounce and all of a sudden be going 1,000 meters per second or kilogram meters per second in the other direction, what's our change? I'm going to call that negative. What's our change now? From 1,000 to negative 1,000. Nicholas is saying 2,000. So that's twice the change in momentum. Okay? Not so good if you bounce off the airbag, because now you're not only going that way, but then you're going back the other way, and you've done the whole change in momentum thing more than you would have just by stopping. So that's one of the reasons they make the airbag cushion you instead of like being a balloon that you bounce off of. Okay? Kind of another way to think about it in that sense. Okay, so that's what's going on with bouncing. Question? No. All right. In science, in physics in particular, we have a number of what we call conservation laws. In other words, if you start with something, whenever you do whatever you do, in the end you have the same amount of that something. Okay? Might have changed form in some sense, but you've still got it. In this case, we have this thing called conservation of momentum. In other words, in some system, like we were talking about before, if something changes momentum in some amount, something else has to also change the same amount of momentum. Okay? Here's an example. You have a cannon. Okay, like the one that I walk by out there and hope that nobody loads it every day, right? Okay, a giant cannon. Initially, how much momentum does the cannon have? Zero, right? Okay, here's your cannon, right, on a little stand. Okay, there's a cannonball in there right now. Zero momentum. 0 kilogram meters per second momentum. You fire the cannonball. Okay? Does the cannonball, once it's going, have some momentum? Sure it does. Let's say it has, I don't know, 10 kilogram meters per second of momentum that way. Something else had to change its momentum in the other direction. If this is on wheels, this is one of the reasons they don't put cannons on wheels, right? Although, I do think they put them on like things that move them back a little bit so they don't like, blow up or whatever. But if it was on wheels or on ice, the cannon would go in the opposite direction, wouldn't it? Because of the force on it. It all goes back to Newton's third law. Cannonball changes 10 kilogram meters per second. What do you think the change in momentum or the momentum of the cannon is? Negative 10, because it's the other direction, but negative 10 kilogram meters per second, because the total has to add up to what it started with, 0. Okay, here's another mind-blowing one. Let's say it's not on wheels. It's actually jammed in the ground there. Cannonball, 10 kilogram meters per second. Cannon can't move. Cannon is connected to the ground. The Earth has what now momentum? Negative 10. Okay. Well, guess what? That's for the entire Earth. Remember how we said the Earth's mass is huge? You can't tell. I mean, you could tell if you were nearby. I mean, let's say the cannonball went off and you were like a mouse living 3 inches underground. You would feel like, right, when the cannonball goes off, or the cannon goes off, not just because of the explosion, partially because the Earth in that area has actually moved a little in the opposite direction. Interestingly, every time I change my momentum this way, the Earth changes a little bit that way. So if I step this way and start moving, guess what? The whole Earth is now having less momentum that direction than before. Can you measure it? No. It's too big to measure. But it is there. Okay? It is there. Mind-blowing. Okay? All right. When a pool ball hits another pool ball, you're playing pool in 11D, right? Pool ball hits another pool ball. If it hits it dead on with no spin, if this one's going along and hits this one, what happens to this one? Stops, right? Because all the momentum is transferred into this one. If this one starts with a momentum of 10 kilogram meters per second, and then it stops, how much does this one have to have? 10 kilogram meters in the same direction, actually. Okay? So we can do some of that. I can actually show you some of that in a second here, which I will do. Okay? Conservation of momentum. In the absence of some external force on the system, the momentum of a system remains unchanged. That's the conservation part. If you start with 10, you end with 10. If you start with negative 5, you end with negative 5. Full stop. Okay? We're going to talk about two different types of collisions in this case, when things bang against each other. The first one is what we call an elastic collision. It's kind of what we call a perfect collision, and pool balls are very much like that. When you have two pool balls and one hits the other and the other goes away, they've got more or less a perfect change in momentum. Okay? An inelastic collision is one that happens with heat and sound. Now, the reason pool balls aren't perfect, one of the reasons, is there is a little bit of sound. When the two hit, you hear a clack. Well, that noise has to come from some energy being released. Well, therefore, the noise part is extra momentum. Where does it go into? Well, it goes into vibrating the air such that it vibrates your eardrum and so on and so forth. Okay, that's where the extra momentum goes. But we're gonna ignore that when we talk about elastic. Inelastic, things like heat and sound and stuff do take place. Okay, turns out the momentum change, or momentum, is still conserved. Okay, so let's see this interactive one if I can get it up here. Let's see. All right, in this case, I want to now go to extras. Let's see. Nope, it's not extras. It is Mastering Physics, Chapter 3, Interactive Figures, Conservation of Momentum. Here we go. Let's see. Let's hope this works. Oh, this is just the cannonball. See how the cannon goes backwards when the cannonball goes forwards? That one's kind of a boring one. Okay, hold on. All right, here we go. Elastic. Let's do elastic collisions first. Okay. You want to? Yeah, you can turn that off if you want. Okay. Actually, I'll turn the other one off too. Okay. Hopefully you can see that way over there, Tom.
Oh yeah.
Okay. This is a green ball and a yellow ball. We're going to give them some velocity. Okay? Let's say, and we're going to give them some mass. I'm going to sit down for this. Let's say we give the green ball, okay? Let's say we give the green ball, let's say we give the green ball just what the default is here, 10 meters per second, and 1 kilogram.
10 kilograms.
That would be, what?
It's 1.
It's 1 kilogram down here. It's a dot. Sorry, there's a period there, decimal in there. It's hard to see. 10 meters per second, 1 kilogram. If we give the yellow one negative 10 meters per second and has the same mass of 1 kilogram, what do you think is going to happen when they collide into each other? Yeah, let's look at how much the initial momentum is. Whoops. The initial momentum is mass P equals mv. Mass times velocity. What is 10 times 1? Okay, this has 10 kilogram meters per second. This way. What is negative 10 times 1? Negative 10 kilogram meters per second, which is this way. What's 10 plus negative 10? 0. So at the end, you better end up with 0, right? The same amount. Now, because they're not sticking together, okay, what do you think's going to happen? And this is what would happen if two pool balls actually hit each other. Would they go boop and stop? If you put clay in there that maybe they grabbed onto each other, sure, or Velcro or something, then they do it, right? They will bounce off. So what is our prediction about the velocity of this one after the collision?
They go in opposite directions. Two constant at the same speed.
How about that? They just exchange momentum. Okay, let's see if that works. All right, so I'm going to hit play here, and they're going, bing, and look at that. Negative 10 here, whoop, and 10 here. Right? Question, Kenneth.
What if there were 10 kilograms going in the same direction that way?
Is that the same direction? What do you mean?
Like 10 kilograms going this way, 10 kilograms going this way. What would happen?
You know what? I can't. For some reason, I can't change this. But it's going to be. It would just make. If they were 10 and 10 kilograms, that would make this one 100 and this one negative 100. And then wouldn't this now be negative 10 and it'd be the same, right? They'd still swap momentums. Yeah. Good question. Good question. Okay. So that's that one. Let's do a couple more and just try to see if we can figure out what the difference is. Let's see. Let's just increase the mass of this one. So now this one's a little bigger. Okay? Its momentum is now 10 meters per second times 2 kilograms. 20 kilogram meters per second. This one is still negative 10 times 1, negative 10 kilogram meters per second. When we collide them into each other, it's going to what? It's going to keep going this way? Well, let's see. This one, well, yeah, let's see what happens here. And we'll check at the end. It's a little tricky to do this math. You have to also conserve energy, so we're not going to worry about that. We're going to check it, though, because I guarantee they did their math right. So let's see what happens. Bing. It went back, but it only went back at minus 3.3 meters per second times 2 kilograms equals negative 6.6 kilogram meters per second. Did I do that math right? Okay. This one now went 16.7 meters per second times 1 kilogram, which is 16.7 kilogram meters per second. What is negative 16.7 minus, we'll call this 6.7 as it turns out? What is it? It's 10 kilogram meters per second. What was the original? 20 plus negative 10? 10 kilogram meters per second. You see how momentum was conserved in that case? Because it started with 10 and it ended with 10. And the reason this is 3.3 is they rounded. So it's about 9.9 or whatever, and they rounded it. But there's a conservation of momentum. Now we also, let's try one more. Let's say that, let's speed this guy. Let's see, we can't speed that one up, can we? It's already going as fast as we can make this one go slower, though. Let's say this one goes, or we can actually, wait, negative 10. Let's say that this one is negative 1. There we go. Okay. Let's try this again. Should we leave that one at 2 kilograms or make it bigger? Leave it? Okay. So we already did this calculation. The momentum of the green one, 2 times 10, 20 kilogram meters per second. The momentum of the yellow one, -1 times 1, -1 kilogram meters per second. What's the total? It's 19 kilogram meters per second. After the collision, shouldn't we end up with 19? Let's find out. Let's see. Bing. Ah, look at this. The green one now is going in that direction. 2.7 meters per second times 2 kilograms. Anybody good at their math there? 27 times 2? 5.4 kilogram meters per second. This one, 13.7 meters per second. Flew out that way. 13.7 times -1. Sorry, I lied. Times 1. 13.7 kilogram meters per second, because it's now going at 13 meters per second, 1 kilogram. What's 13.7 plus 5.4? 19.1, which comes from rounding errors, it's the same. Isn't that cool? Conservation of momentum. Okay. If we made this one really big and made this one going the opposite, well, let's just have it go, I don't know. Let's make it 0. I can't make it 0. Yes, I can if I'm good. Almost. Oh, there. Okay. Well, let's see. Let's see if we can figure this one out. Well, we'll do the same calculations. 10 meters per second times 10 kilograms. 100 kilogram meters per second. 0 meters per second times 1 kilogram. So the total is 100. So at the end, the total should still be 100. Okay, let's try it. Oops, sorry. Okay, let's try it. There it goes. Bing. Okay. 8.2 times 10. 82 kilogram meters per second. 18.2 times 1. What's 82 plus 18? 100.2, because of some rounding errors, and there you go. Okay? So it's conservation of momentum. All right, interesting.
If three things hit each other, like in like a triangle, would they still all add?
Good question. So Eric says, what happens if 3 things hit in order? Then it gets really tricky. In fact, there's lots of like physicists who still think about these problems. They're called 3-body problems, where you have 3 different things interacting with each other. But let's say you had 3 different things coming in. This one's got a momentum this way, this one's got a momentum this way, and this one's got a momentum this way, and they all kind of hit right there. Boom, boom, boom. If they hit at the same time, yeah, figuring out what the result is would take a whole bunch of math. Louis said he's going to do it tonight, but a whole bunch of math, right? So, but yeah, it's definitely would all, in the end though, if you added the momentum of this and momentum of this and momentum of this at the beginning, wherever they ended up going, like let's say this one went off this way, and this one went off this way, and this one went off this way, if you added all those up, it would be the same. So, yeah, good question. And same with 1,000,000 particles. Okay?
So
all right.
Is there ever a point that it would just hit it and stop dead in its tracks while the other one absorbs all of the energy?
That's inelastic collisions, which we'll talk about after the break, which we'll go to a break now. Did you have a question?
Nope.
No. Okay. Let's take another 10. Okay. Hey, Louis, you want to hit the lights? Thanks. Okay. So earlier we were doing elastic collisions, where we had perfectly colliding bodies. No heat was lost. They didn't squash into each other, anything like that. In this case, we're going to talk about inelastic collisions, which means we do have things squashing against each other and deforming and creating excess heat and so forth. Okay, but we still have conservation of momentum. In fact, let's see what happens here. where we have equal amounts of momentum in both trucks. Okay? We start out 10 meters per second times 1,000 kilograms. What's the momentum of this guy? 10,000. What unit are we using? Kilogram meters per second, right? Kilogram meters per second. Okay. What's this one? Negative 10 times 1,000. Negative 10,000 kilogram meters per second. 10,000 plus negative 10,000? 0. So at the end, we should have 0 total. Now they're going to collide and stick to each other. So watch this. If they stick and there's 0 momentum between the two of them, what do you think the velocity is going to have to be? It's one thing, and now it's going to be one thing of 20,000 kilograms. Even though it's two trucks, they're going to collide, and we're going to pretend it's one 20,000 kilogram mass. And if it's got 0 momentum, what's the velocity going to have to be? 0. So let's see. There they go. Hope they've got their seatbelts and airbags. What's the end velocity? 0, because the total mass is 20,000, and if it's got 0 meters per second, it's 0 total momentum. So it works. All right, let's try it this way. Let's say we have a 2,000. I like how it changes the size of the truck too. 2,000 kilogram truck. 2,000 kilogram truck. 2,000 times 10. 20,000. 20,000 plus negative 10,000? 10,000. So that's what we should end up with. Okay? We can actually probably predict this relatively easily. In the end, if the total mass is now 3,000 kilograms, and we know that we're supposed to end up with 10,000 kilogram meters per second, we can do a little bit of algebra. I know that's a dirty word around here. Do a little bit of algebra and say that if momentum equals mass times velocity, and we know the momentum and we know the mass, can we figure out the velocity by dividing both sides by mass? Velocity equals the momentum divided by the mass. What's 10,000 divided by 3,000? What's 10 divided by 3? 3.33 meters per second. And it's a positive number. So let's see, if this guy's going that way and this guy's going that way and they collide, which way are they going to end up going? That way. Let's see if it ends up being at 3.33 meters per second. Oh no, oh no, oh no, oh no, bing. And there we go, 3.33 meters per second, because momentum is conserved. Okay, want to try another one? Can't have the, let's see. If the truck is going, let's say that the little truck knows that it's going to get hit, so it starts backing up at 2 meters per second. I think it's going to back up at 2 meters per second. And let's say the big truck is now big. Okay? I'd back up too. Okay, let's see if we can figure this out. Yeah, let's see if we can figure this out now. 10 meters per second times 10,000. 100,000 kilogram meters per second. That's big. This guy? 2 times 1,000. 2,000 kilogram meters per second. But it's also that way because it's backing up because it's about to get squashed. So what's the total? 102,000 kilogram meters per second. Let's use the same thing before. Now the total mass is what? 10,000 plus 1,000. How about 11,000 kilograms total, right? And we know that the total momentum is 102. So now we're going to have to use our calculators probably. 102,000 kilogram meters per second divided by 11,000 kilograms. How about I use the fancy calculator I got built in here? Oops, what did I say it was? It was
9.27.
Is that what it is? 9.27? Okay. So we're going to hope that the final velocity is 9.27 meters per second that way. In other words, this guy didn't slow down too much when it hit this tiny little truck. especially when the truck was backing. See if it works. Backing up, backing up, backing up, backing up, backing up. Boom. 9.27.
After time, would the red be separating from the green and be going faster?
If they stick together, no. Let's say it's perfectly inelastic, meaning they stick together. No. It could maybe in real life. There's probably some elastic portion, so it's going to bounce back. But no, if it sticks together, then it sticks together. Let's pretend there are Velcro on the bumpers. Yeah. Okay. So do you guys believe, at least according to this demonstration, that momentum's conserved? Okay. Not too hard to figure out once you know some of the math, and not that much math.
So where do you see inelastic collision in nature?
In nature, all collisions are somewhat inelastic. In other words, there's no perfectly elastic collisions in nature. They say that when atoms bump into each other, that's perfectly elastic. There's really no sound. There's really no heat lost. It just doesn't make sense. So in real life, that's probably the only place you see elastic. Inelastic are everywhere. You see when they partially collide with sticking together. Fully inelastic, rare. Velcro. I mean, if you were to, let's say you're standing out here in Djibouti on the road and some guy comes along and smacks you and you end up on the hood. Well, you really are part of the car now, right? So that's a perfectly inelastic collision. Okay. You're not too happy, but perfectly inelastic. Okay. All right. So, let's see. There we go. All right. Sorry, can't read the bottom here. Okay. So we talked about elastic collisions and inelastic collisions. I may ask you the difference, but really the difference is elastic collisions are where there's no heat and no sound released during the collision. Not real life, except maybe at the atomic scale. Inelastic collisions are lasting deformations or heat or sound or whatever. Okay. That should say completely inelastic collisions. I'll have to change that. Results in two bodies fusing together as one. Okay, so that was momentum. Sometimes it's easy to get confused with momentum and energy. Okay? Energy is a huge, huge topic. You could teach an entire class on energy. We're only going to talk about a couple little bits of it. You guys all know the formula, E equals mc squared. You know what the E stands for? Energy, right? So Einstein was thinking about this stuff. Okay, this is what makes nuclear bombs happen and nuclear power happen. And in fact, it's what basically makes anything happen. We talked the other day about perpetual motion machines that are illegal, that are not illegal, they're impossible. They're illegal too, but no, they're impossible. That's all about energy and this conservation of energy, which we'll get to. But my initial question here is, how much faster will you hit the ground if you fall from twice as high? Okay. Now, you could actually tell me this based on what we talked about before, right? You could figure out twice as high. You'd have to do a little math and some, figuring out of those equations. We could do that. But we're going to use energy considerations to figure this out in this chapter. Okay? This definition of energy, physicists kind of hate this definition because it's what we tell all the beginning students like you guys, and it doesn't really tell us that much when you get down into the weeds. Okay? I mean, it just doesn't give you enough information. But for what we're worried about, it's fine. Energy is the property of a system that enables it to do work. In other words, it enables it to do something productive, if you will. Well, it doesn't even have to be productive, but we've got to define work as well. Work is defined as a force times a distance. Impulse was force times, remember? Time. Force times time was impulse. Now we're talking about work, which is force times distance. Here's an easy way to think about it. If I take this book, right, and I move it upwards, don't I have to push up with it more than gravity pulls down? If I'm going a constant speed, I'm pushing it up the same amount as gravity is pushing down, because it's constant speed and its net force is 0. The amount of work I do on the book to lift it is just equal to the distance I lifted it times the weight of this thing. The force that I push it up times the weight. If you've ever climbed stairs, you'll know that you get a little tired because you're doing work on your body to lift yourself, or climbed a mountain to lift yourself up. Okay? Okay, this is what work is. So energy is the ability to produce a force times some distance. We'll get to the details of that in a few minutes. Okay? We just have to be careful about what we mean by distance. If I'm holding this book like this, and I'm moving it sideways at a constant speed, what force am I putting on it sideways? At a constant speed. It's like we need to learn last week's material again. Constant speed. If I'm pushing, how about the horizontal force? You're right, I'm pushing upwards on it, but the force sideways is how much? 0, right? Remember how it's 0? Everybody by now, hopefully you guys are getting this. If I'm going sideways at constant speed, Newton's first law says it's going to keep going at a constant speed without me putting any net force on it, meaning, except for a tiny little air resistance, there's no other force this way on the book. If there's no force in either direction, can I do any work on the book? Force times distance, 0 force, 0 work. Moving a book sideways does no work on the book. Just like holding the book here does no work. I am pushing up with the force of gravity, right, on it, because I have to hold it up there. But how much distance am I going right now? 0 distance. How much work? 0 work. So it's why work's defined a little weird, because it does get tired. I mean, you guys in boot camp ever have to hold the rifle out when they do something stupid, right? Right? Or even when you do something right, they just still make you do that. The drill instructors like that. You get really tired, right? How much work are you doing on that rifle? 0, because you're not moving it any. It's not no distance. But you're doing work in your muscles. Your muscles have to kind of continuously tense up and go back and tense up. That is doing work internal to your body. We're only talking about external work here when we talk about doing work on the book itself. So we got to get that kind of through our brains. That takes a little while to percolate through. But yes.
Does that translate to energy? That it's not taking any energy to...
If I hold the book like this, it does take energy that's internal to my body, right? Because I get tired. And really, I eat food, and that turns into energy that turns into well, I don't even remember all the biology, but it turns into ATPs and ATP and all that. And I'm expending energy. How do I know I'm expending energy? Because I get tired and I warm up a little bit, right? I mean, if you're holding this book out here, you're going to start sweating a little because your body's got to use energy to actually hold the book up there. Okay? So yes, it's internal, but as far as the book's concerned, no work's being done in the book. We all clear on that? No work done in the book right now. Work done in the book when I raise it because I'm pulling against gravity. No work done when I go sideways because there's nothing else pulling sideways. Yeah?
But there is work being done when you begin to move it sideways.
Yes. Very good point. Right the instant I start it, I have to accelerate it a little. So there is a little bit of work. Yeah. And then when I stop it, I kind of get that work back, actually. It's like the book does work on my hand in the opposite direction. So that's why it all kind of works out. But okay. When you push a crate across the floor, you do work, but you don't do work when you carry a book at constant speed across the room. Why on the floor when I push it at constant speed? Friction, of course, okay? Because there is a force the other direction. So that's when you have to do work to do it. Okay, it's all about that. All right. Energy and work. Work is force times distance. If you lift 2 boxes up a 1-story house, you do twice as much work as if you lifted 1. So I take these 2 pens and I lift them from here to here. That's twice as much work as though I lifted 1 pen from here to here. Why is it twice as much? Because it's twice as much force. Remember how twice the amount of mass gives you twice the amount of gravitational force? Twice. It's all about, it's all about this direct relationship. Force is twice as much. If you lift 1 pen from here to here, it's twice as much to go there, twice as much work. again, it's a direct relationship. You've done twice the distance, twice the work. If it's twice the force because there's 2 pens, twice the work. Not very hard stuff, just kind of conceptual stuff. Okay? How much work do you do if you hold the heavy weight on that weight? 0. Okay, no distance. Plenty of force, no distance in that case. Okay. All right, how much work do you do carrying a heavy weight at constant velocity around the room? We talked about that. Constant velocity around the room. Any work done on it? No. Big difference between the work done on an object to the work done to hold an object internal to your muscles. Already covered that. Okay. All right, so that's the overview of work and energy. There's this thing called potential energy. Sometimes an object can store energy because of its position. And I'm using position kind of broadly here. If I hold the pen like this, if I drop it, can it do work on the ground? If it bounces, sound. Let's take a hammer. Let's take a rock, a big rock or a brick, and we put a little nail that's just sitting in the ground. If I drop the rock onto the nail, won't the nail go into the ground a little? If it's ground, right? Well, it did work on the rock, on the nail, because it moved the nail, pushed the nail with a force for a certain distance. So yes, so a rock or this pen does have energy based on how high it is. Now, it's very subtle. Does the pen have more work when it's over the floor at this height or over the table at this height?
Over the floor.
Over the floor, because it can go farther, right? So really, you got to be careful. You got to define your system right. I mean, because it's a little weird. It's not like anything changed about this. It didn't somehow like get more energy just because I moved it over the table. It got more energy because now the table would stop it before the floor stopped it. So it gets a little crazy there. But otherwise, as far as it is, let's say the floor is always the floor 2 meters below the ground, then this has a certain amount of energy based on being this high. If it's this high, less energy. Potential energy. Other things that can have potential energy. A spring. You compress a spring together, right? And you put a rock on the end, boing, it does work on that rock. That energy is stored in the spring inside kind of the atoms and molecules that makes it hard to compress. It's made of a material that is pushing kind of against itself. Tyler's giving me a look like I'm crazy.
No, I was wondering if max potential energy is going to be kinetic energy.
Ah, good question. So yeah, that's a very good point. Hold that thought. Tyler's thought was, does max potential energy equal the kinetic energy you can get? Hold that thought. We'll get to that in a couple minutes. A very good point. Gravitational potential energy is this stuff as high, the higher you lift, the more energy it has. Why is it called gravitational? Because if you drop it, what causes the force? Gravity, right? So it's gravitational potential energy. If you have a bow and arrow, same thing. Once you have the arrow holding it there, it's got potential energy to do work on that arrow, right? And then that arrow all of a sudden has energy, a different kind of energy, which Tyler just mentioned, and then that can do work on something else. So it's all this big system. Okay? All right, we already kind of mentioned this. The amount of force necessary to move an object up is just its weight. The weight is the force of gravity. Force is mass times acceleration. We said acceleration is g. Mass times g is your weight. So if you want your weight, you take your mass, you multiply it by 10, and you get your weight. Okay? And that is also that times the height that you go. mgh gives you the potential energy. Whew, that's it for the math for this part. Okay? But really it builds on itself. The weight is mg, the height that you lifted is h, mgh, height, that gives you the potential energy. We measure potential energy, one sec, Tom, we measure potential energy in this thing called joules. Okay? Where do joules come from? It's just it's the metric form for energy, which we'll talk about. Yes, Tom?
Now, is potential energy in force, is that the same concept as potential energy in food with calories?
it is the same. Energy is energy. And in fact, if you look on, I don't know if these bottles listed in joules or kilojoules, sometimes instead of calories, they list things in, yeah, they, no, hang on. I can't tell on this one. Well,
I have an Emirates one.
yeah, sometimes they list them in a different, the amount of energy versus calories is sometimes listed in joules or kilojoules. Okay, joules are just another type of energy. Now, to answer your question, yes, it's the amount of energy. The way they get the amount of calories in food is they basically burn it. And they say how much energy is released when you burn it. That's how many calories it has. Because basically that's what your body does. It doesn't physically like flames come out of your stomach or anything, right? But it burns it in that it changes its form to something else that it can use. Okay? All right, that's joules. That's what energy is measured in the metric system. Anybody know what it's measured in? Well, we already talked about it. In the English system? Well, we just talked about it. Calories? Yeah. Calories or kilocalories. Okay. Okay. Here's an interesting one. Does it matter how I got somewhere for the amount of potential energy that it has? Does it matter if I do this to the pen? If I go straight up, it's got some potential energy. Or if I go over, up, and over to the same exact place, does it have a different amount of potential energy? Same amount. Why? How much energy do we, or how much work do we do going this way? 0. How much work this way? mgh. That's how much. How much work do we do going this way? 0. It doesn't matter. So it doesn't matter if you lift something from here to here. It's got the same potential energy as if you went up a ramp. And it's got the same potential energy if you went boom, boom, upstairs to get to the top there. Same amount of potential energy. It's the same distance. It's the same weight. Same amount of potential energy. Doesn't matter how you get there. Once you get there is what matters. Okay? The work done elevating the weight is the same in each case. This is potential energy. Okay. Oh, I lied. That was your last break, sorry. Meaning I'm going faster than I thought. It's good. Tyler briefly brought this up a second ago. Kinetic energy. Kinetic means motion, right? Kinetic basically means motion. Kinetic energy is energy because something's moving. Very similar in some sense to momentum, but now we relate it directly to the amount of work that can be done. Not the amount of impulse or momentum change or anything like that. It's just the amount of work we can do. An object has kinetic energy if it's moving and it has mass. Okay? The kinetic energy depends on simply the mass and its speed. All right, we've seen something similar to this formula before, but not this formula. I am not going to define it for you unless you want me to, but we're going to, or we can talk about it offline. This is what kinetic energy is. 1/2 times the mass times the velocity squared. Okay, don't worry about how we get to there unless you want to look it up. It might be in your appendix of your book. Okay, but kinetic energy is just energy, so we also measure it in joules. Okay, all right. Bobby and I were talking about this earlier. If you throw a ball, your hand does work on that ball, right? Because you got to get it up to speed. Okay, if it was constant speed, no. But if you're trying to accelerate a baseball, your hand is doing work on that ball. It's got a force times the distance. It does work, correct? Work. It does work on the ball. Once the ball leaves your hand, well, the whole time, but once it leaves your hand, it's got energy. Can that ball now hit somebody in the head and do work on their head by moving side, right? Sure can. Sure it can. So we've given it some form of energy, not based on its position, but based on its speed. Okay? The kinetic energy, okay, is equal to the amount of work it's needed to bring it to rest. Why is it that? The amount of work you did to start it gives it a certain amount of energy. The amount of energy it has is equal to the amount that it would take to stop it again. Kind of simple in that sense. Not that hard in the sense that, oh, if I give it some amount of kinetic energy with some force, it needs the same amount of energy to stop. So I give it that energy, it needs that same amount of energy to stop again. Make sense? Not too tricky. Okay? And the amount of work necessary to stop it would be that force times distance again. Here's where that force times distance comes into play again. All energy. Potential energy, where it's located in space, or its molecules that are compressed or whatever. Kinetic energy, energy based on motion. All right, we're getting there on this. Aha. Kinetic energy, 1/2 mv squared. The velocity here is squared. What was the question I asked right at the beginning of this? Do you remember? If I drop something from twice as high, right? How much faster is it when it hits the ground? Right? It's not twice as fast, actually. It's actually 4 times. Okay, because it's squared. If it was 3 times higher, it would be 9 times as fast. Twice as fast, it can do 4 times as much work because it's got a squared value in there, which is interesting. Okay, if it's 10 times as fast, it can do 10 squared, which is 100 times more work. This is why the faster you get something, the much more work it can do. Here's an interesting one, and this is like the kind of the real life one. If you're going twice as fast and you slam on your brakes so your wheels stop and you just skid along the ground, if you go 4 times as fast, it takes, or sorry, if you're going twice as fast, it takes 4 times as far to stop you. It's because of this energy-work relationship here. If you're going twice as fast, it takes 4 times as long to stop. And they taught you this in like driver's ed, right? I mean, I don't know if they taught you that specifically, but they teach you that like if the faster you go, the farther ahead of time you have to think about stopping if you're going to want to stop, right? And it's all because of this idea that you double your speed, you've got it takes you 4 times as much time or distance to stop. Okay? It's what?
Boat in the water.
Boat in the water, exactly the same thing. Yeah, yeah. Well, more or less the same thing. Yeah. If you're going twice as fast in your ship, 4 times as long to stop. If you're equally, the same amount of force going backwards on it to stop it. Yeah. Yeah. So real life. So this guy's. It'd be kind of cool if your car really did that when you stopped.
Do that in Compton.
Yeah. What's that?
They do that in Compton.
They do that in Compton, right? All right. Kinetic energy, potential energy. Okay. Now we talk about another conservation law. Okay. Conservation of energy. It's another one of those things that you don't want to try to argue against, because you can always, as far as we know, conserve energy. It's a little harder to deal with it because you've got heat and sound, which is energy, basically, which can easily dissipate. So you might lose track of it pretty easily, but it's definitely still there. Okay? I'm going to do a little demo here with a pendulum. Now, let's think about what's going on here with a pendulum. Pendulum is just a little, well, we talked about it last week. Yeah, oh no, you're going to talk about the little balls things? Those things are cool. Also conservation of more momentum than energy in that case. Yeah, Louis just brings up a good point. You know the little system where it's got 4 balls like this, and you bring one back, and then you let it go, and then one on this side goes. And if you do 2 back, then 2 go on the other side. And if you bring 3 back, then 3 go on the other side. It's pretty cool. It's all about conserving momentum and energy in that case. And it's kind of cool if you do that. I don't think I have one of those. Maybe there's one I don't know where I'd find one around here. Anyway, pendulums just go back and forth. Now, when a pendulum is up at the top, when a pendulum swings all the way up and then stops, isn't it some height above the ground? Well, that height is potential energy. And then it starts swinging back down again. As it's swinging back down, it's got both potential energy because it's still above the bottom point, and it's got kinetic energy because it's moving. At the bottom point, we'll say that that's the floor, like it just touches the floor. It's all kinetic energy. And then it starts going back up again, and it gets up to the top. It's got potential energy again. So it's a conversion, right? From one to the other, back and forth. Starts with potential energy, kinetic, 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 all kinetic, more potential, more potential, more potential, and then back and forth and back and forth. Let me bring up a little demo, if I can find this one, on the interactive pendulum. Okay, let's see.
So if that pendulum came to a dead hang, would that all be due to air resistance?
Yes, if a pendulum stopped moving, it would be due to air resistance and friction in the little thing that's holding it at the top. Both of those would cause it to stop. And that's a... What's that? In a vacuum with a perfectly smooth thing at the top, it would go forever. Yeah, if it could. I mean, it would go for a long time. And Tom was talking about one he saw at a museum or something where Portland Convention Center, which goes for days and days at a time without redoing because it's got so little friction and it's a big mass. Let's see. Interactive figures. Is there a pendulum in here somewhere? Energy transitions in a pendulum. There we go. Hey, there's our pendulum. Okay. This is actually not math so much as graphing, but I'll explain it as we go along. You can actually lift that up and then let it go. And the total energy, in other words, the potential energy plus the kinetic energy is conserved. If it's conserved, it's just like the total with the momentum before. Remember how the total always stayed the same, beginning to end? The total here should stay the same. So if we're talking about an energy, a line that doesn't go up or down, it's going to be straight across, right? So the red line here, which is total energy down here, should stay the same. Okay? Potential energy is going to be a green line. Kinetic energy is going to be a blue line. Okay? And just so we don't confuse us, get rid of the little... The green line's all over the place? Okay. With that, if I start it, take a look at the different lines. It's at the bottom. It's at the top. It's at the bottom. The red line, constant, staying the same. The blue line is the kinetic energy. It's bottom, zero kinetic energy, maximum kinetic energy. Zero kinetic energy, maximum kinetic energy.
So the green and blue lines cross when it's about halfway between the top and bottom.
Exactly when there's halfway between, yep, as it turns out. Okay, it starts over. But you can see now, if you watch the green line, you'll notice the green line gets to its maximum when it's at the top, when it's got the most potential energy. And the blue line gets its maximum when it's got at the bottom, when it has the most kinetic energy. And the red line says it's always the same. Okay, it's just a conversion of energy back and forth to each other. Okay. All right. So that's that demo. I have another demo that I'll show you, or a video that I'll show you as we end in a couple minutes. And I want to show you that. Let's just go through a couple more things here. I wish we had time to do this right now, but this is another one. Roller coasters are a great way of converting energy between potential and kinetic. Ever been on a roller coaster where you sit in the little seat and you go and you start out and immediately you go to this thing that starts you going up and it goes click, 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 all the way to the top? And I don't know if you've ever noticed, but that top of that first thing is the highest you'll get, unless you have more click, click, click somewhere along the way. Why is it the highest? Because that's where the maximum energy is. And like Tyler said earlier, when you're converting energy back and forth, you can never get more total. So right at the top is the most you're ever going to have. And so you can't actually go higher. And this is the demo that I'll show you in a minute. But here's, what's that?
Is the loop just to help keep the energy going?
The loop is so you have fun, right? But it does, the energy transfers do it. If we were to answer all these questions, how much total energy does the cart have? Is it moving up here? It says it's 10 meters per second. Can we do 1/2 mv squared to find out the energy, the kinetic energy? We could. We're not going to because it's too much math. We're just not going to worry about it. 800 kilograms times 1/2 is 400 times 10 squared is 100. So I guess we are going to do it. It's 4,000, right? 4,000, the kinetic energy, 4,000 joules of kinetic energy And the potential energy, mgh, m is 800, g is 10, so that's 8,000. Height is 80 meters, 64,000, right? 64,000 joules of potential energy. I think I did this one wrong. 10 squared is 100 times 800, 8,000. No, that's right. That's right. So the total is going to be 68,000 joules. Total. And that can never change. Okay? Can never, the total can never change. That's all we're going to do with that part. But that's how you'd figure out that. How fast is the roller coaster traveling initially? 10 meters per second. Okay? Oh, how fast is the roller coaster traveling initially? That's an odd question. That shouldn't. It is 10. It's just written there. How fast is the roller coaster traveling at the bottom of the hill? This one we would have to figure out. If we know the total energy, and we know that it's subtracted out the amount of potential energy, where does all that potential energy go? Into the kinetic energy, into its speed. This is why, as you go down here, you speed up. Down here, you're as fast as you're ever going to get, right? And all that potential energy turns into kinetic energy. We could figure that out. We'd have to do a little square root of this thing. Don't worry about it. Okay? Around the loop, up here, it slows down a little bit. As you're going around that loop, you're slowed down a little. And then you speed back up again. And then here, as you go up this hill, you slow down a little bit, and you get to here. So we could answer all these questions if we really wanted to. I'm not going to make us go through that because of time. I want to show you this little video. But we could do a lot of these calculations figured out. But it's all about potential turning into kinetic, turning into potential. Potential turns into kinetic, turns into potential, turns into kinetic, turns into potential. All conserved. Okay? All right. Pendulum interactive did that. Bowling ball video, bowling ball video. Okay. So here is a video. Oops. That I want. Oops. I want to show you with videos. This is the author of our book again. And let's see. Bowling ball conservation of energy. I'm going to show you this guy, then the other guy.
Been brushing and flossing your teeth, keeping them nice and healthy, huh? Not going to do much good if this 14-pound ball comes crashing through them, yeah? Watch this. I want to show you a nice physics demo.
Watch this. He doesn't.
The ball doesn't smash my teeth. How come? How come? Because of a very important conservation principle called conservation of energy in physics, which states this. Take some energy to lift the ball, yeah? Now it has energy of position. Call that potential energy. I let go. It turns into energy of motion, kinetic. Back to potential, kinetic, motion, but no more potential energy afterwards than that which I start with. Try this sometime. Give the ball a little push.
You don't want to do that.
You better move your head. You know why? Because you gave it some energy in addition to the potential energy, and it will come higher.
And this is the big key here. With the bowling ball, I was trying to figure out how I could get some weight like hanging here. Maybe I'll try it at some point. Maybe through there. But the bowling ball will never go higher because it's got potential energy, and that's the only energy it has. And remember, the total is the potential plus kinetic. So if you let it go, it gets lots of kinetic energy, potential, lots of kinetic energy. Can it ever gain more to get higher than it started with? No. So as long as you don't move your face, it's okay. So I think it's here. There's this guy who worked at MIT. He was a physics professor there. And he does this experiment. There he is. Oh, you're getting kind of a, there it is. I think. Okay, whoops. Let's start it here. He does this same experiment. I think it's a little bit better done than before. Okay.
That's okay.
Oh, it's not loud enough.
Now comes an experiment.
Can you hear it okay?
Which is emotionally the most difficult to do, which is cognition. I'm going to put my life on the line to show you that I'm really a believer of the conservation.
He's really a believer of the conservation of energy.
And you will see how I'm going to do that. I'm going to take the place of the glass. And I'm going to hold this object at my chin, and I cannot move any further back, so there's no cheek here. I'm going to release it right from my chin. You realize, as you have just seen, that the slightest push, and this will be my last lecture, and no book signing afterwards. So I need your collaboration. When I count down from 3 to 0, no noise, no coughing, and I would even appreciate it if for those 3 seconds you would not even breathe.
Don't even breathe.
And I have to tell you something. I couldn't sleep all night.
Couldn't sleep.
I'm going to close my eyes. I don't want to see it. And I'm going to count down from 3 to 0.
So there you go. Same sort of thing. This is actually a pretty fun video to watch all the way through. He does some cool other experiments with pendulums, as it turns out. Okay, so famous MIT professor.
What's this book called that you have over there?
For the Love of Science, I think it's called. I put the video link on my website too. Okay, last thing for the night. And I do want to, there's one more little video clip that you've all probably seen before. When you walk up a hill, you do some work to get yourself to the top. We've already said that it doesn't matter if you walk up a hill or run up a hill. It's the same amount of work once you get there, or the same amount of energy, meaning the same amount of work once you get there. What is different about whether you walk or whether you run up a hill? Your speed? The time. It has to do with your speed, sure, but it has to do with the amount of time it took. Power is the amount of work divided by the amount of time it takes you. Okay? Power is simply how fast work is done, and that's really what gets you tired, because your body has to expend a lot of energy very fast. And that's the part that your body can't recuperate that fast. If you're just kind of meandering up a hill or set of stairs, your body can recuperate pretty fast. It doesn't get lactic acid buildup, etc., right? But if you do it quickly, your body just can't produce enough energy in the amount of time necessary, and you get winded and you get tired. Okay? Power is the amount of work divided by the time interval. Okay? Power is measured in watts. And what's a watt? A watt is a joule energy divided by a second, a joule per second. It all comes back to, like, physicists don't try to trick anybody, right? They say, look, the work done by the time interval, joules divided by seconds. Okay, that's how much power something is. And if you happen to go to the gym and you're doing the little the exercise bike or the treadmill, it'll tell you how many watts you're burning at a certain amount of time, how much energy you're expending in that amount of time. Okay, we used to measure power in horsepower, right? Number of horsepower, and you can convert it if you want. 1 horsepower is 746 watts. Okay, and anybody remember Back to the Future? Okay, they actually use that. You probably didn't know that whenever you watch that movie, that sometime in the future you'd watch, or you'd talk about watts again, and thing. But let's listen to this little video. I actually found an HD version online of this clip. Right.
Hey, Doc, this is it.
Never mind that now. Never mind that.
Why, that's me. Look at me. I'm an old man.
Hey, I'm Dr. Emmett Brown. I'm standing here on the parking lot.
Thank God I still got my hair. And what on earth this thing I'm wearing? This is a radiation suit. Radiation suit? Of course. Because of all the fallout from the atomic wars. This portable television studio. No wonder your president has to be an actor. He's got to look good on television.
Whoa, this is it. This is the part coming up, Doc.
But I need a nuclear reaction to generate the 1.21 gigawatts of electricity. What did I just say? This sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity. 1.21 gigawatts! 1.21 gigawatts! Great Scott!
What the hell is a gigawatt?
How could I have been so careless? 1.21 gigawatts! Tom, how am I going to generate that kind of power? It can't be done, can it?
Look, all we need is a little plutonium.
Oh, I'm sure that in 1985, plutonium was available in every corner drugstore, but in 1955, it's a little hard to come by. Marty, I'm sorry, but I'm afraid you're stuck here.
Whoa, Doc, stuck here? I can't be stuck here. I got a wife in 1985. I got a girl.
Is she pretty?
She's beautiful. She's crazy about me. Look at this. Look what you wrote here, Doc. I mean, that says it all. Doc, you're my only hope.
Marty, I'm sorry, but the only power source capable of generating 1.21 gigawatts of electricity is a bolt of lightning.
What did you say?
A bolt of lightning. Unfortunately, you never know when or where it's ever going to strike.
We do now.
This is it. This is the answer. It says here that a bolt of lightning is going to strike the clock tower at precisely 10:04 p.m. next Saturday night. If we could somehow harness this lightning, channel it into the flux capacitor, it just might work. Next Saturday night, we're sending you back to the future.
There you go. Back to the future. 1.21 gigawatts, we would call it today, instead of gigawatts, I suppose, is a lot of energy. So anyway, so that's power. The last little 1 minute thing we've got here, where does all the energy to power our AC units come from? Diesel generators, which burn diesel fuel, which comes from where? Comes from oil, which comes from where? Fossils come from dinosaurs, right? Dino juice, they call it, right? Where did the dinosaurs get their energy to produce muscle to run around and chase other dinosaurs? Plants. Where did the plants get their energy? From the what? From the, well, not really from the ground, but kind of from the ground. They either ate other animals, or the other animals ate plants. Where did the plants get its energy from? Or I already said that. Where did the plants get their energy from? The sun. So really, diesel fuel is solar power.
There you go.
If you want to think about it like that, but it is finite because we don't have that. We don't have an infinite amount of oil in the world, right? The only real, well, there's really only two sources of energy that are not based on the sun. Any ideas which ones? Water actually is. How does the water get up into the mountains to go down to create the rivers that produce the waterfalls? Evaporation. What evaporates the water? The sun. Same thing. Windmills. Windmills, well, why does wind occur? Wind occurs because there's different pressure areas, right? And the pressure is caused by heating and cooling of the areas around the thing. One more chance. Nuclear, right? Nuclear is the big one. The other one, there are some nuclear forces underground which heat up the ground itself, but nuclear is the big one. Okay, so that was the other one. Oh, I guess it's nuclear as well. Yeah, I guess it's nuclear. So I was thinking some sort of like hydrothermal power, which is really nuclear, I guess. So nuclear or the sun. And by the way, the sun is nuclear fusion. So really it's nuclear. But anyway, all right. I tell you what. We're going in 1 minute. We're not going to do the check questions. That was a long class again. There is a homework assignment on the mastering physics. It should take you less than an hour to do. It's fairly simple questions. If you can't log in, if you've tried to log into Mastering Physics with the ID that I sent you, and you can't, come on up here after class and we'll check it out. Or you can try again tomorrow and we'll just do it tomorrow night. Either way. Lab is tomorrow. Please bring your lab books. That's the skinny one. This one. Want to hold it up? Thank you. James is holding that up. Take a look at that. If you please bring that. I'll try to have a couple different kind of shorter labs. I do not think we'll be here for 4 hours tomorrow night. We will have one other student who I haven't even met yet, just doing the lab. And that's about it. All right, we'll see you guys tomorrow. Any last minute questions? The assignment is online. It's chapter 2. It's got a due date and everything. Sign on, you should see it. If you don't, try it tomorrow. If you don't, if you're going to have problems connecting to a computer, let me know too. Like if you don't have a computer at home or one at work that you can use for an hour after work or whatever, let me know. Okay? I'll probably make the assignment due either Monday or next Saturday. See you guys later.